So doing that now. I think we're good there. Minimize this and we'll be in good shape. All right, let's do it. All right, welcome everybody. I am Ryan Hoger with Temperature Equipment Corporation. I am flying solo today, so I am both producing and doing the presentation. So that means I'm reading questions from you guys simultaneously with presenting. So if I miss your question for a minute or two, just give me a second. When we get to the quiz questions, I'll go back and double check to see in case I missed anything. The quiz questions, if you're needing a PDH certificate for professional engineering license, you do need to answer those questions and answer them correctly. If you don't need that certificate, you're still welcome to answer the questions just because sometimes it's fun to see if you guys get the answers right. I mean, fun for me, at least. All right, if you didn't know what you signed up for, this is an indoor air quality seminar for commercial buildings focus. It is 3 hours long, which I know is absolutely huge, but there's a ton of people who need CEUs, plug my laptop in, who need CEUs before the deadline here in February in Illinois. So we're trying to get as many as possible. We will take a break part way through. So I don't know exactly, it just kind of depends on how it works out, but like an hour and a half through, we'll take like a 10-15 minute break and then we'll resume back up. I'll let you know when we get to that point. And with that, we're gonna go ahead and do the fun stuff. All right, so here's kind of our agenda for this morning. We'll talk about indoor air quality pollutants just a little bit so everybody's on the same page with some of the stuff floating around in the air that we want to get rid of. And then we'll go into the solutions for that. First, we'll take a discussion on ventilation. We'll talk about what's required from a code perspective for ventilation. And then we'll talk about how demand control ventilation works to save energy and sort of its place right now at the moment with COVID being around. And then we'll go into all the germ stuff. We'll talk about all the different technologies that we can use to eliminate germs in the building, including COVID-19, obviously, because that's been the discussion for almost 2 straight years now. Can't believe it's been 2 years. And then we'll talk about some other miscellaneous things that kind of just tie everything together. So that's kind of our agenda here. You see that pyramid over there. I don't remember exactly. Well, I stole it from Carrier, obviously, because you can see the Carrier logo. But I don't know if they made that or if they stole it from somebody else. But I've seen it or similar versions of it in numerous places. And so we're gonna kind of build our thing that way, right? Starting sort of kind of from the bottom up, if you will. The most important things are, well, you have to operate the HVAC system, obviously, otherwise you're not going to have any of this stuff working. So that kind of goes without saying. But ventilation air, outdoor ventilation air for dilution control, humidity control, filtration, and then air cleaning technologies are kind of the pyramid here. It doesn't make sense to buy some cool UV light or bipolar ionizer or something like that, and you haven't even done the basics like dehumidify the space or ventilate the space, right? Those core things that we've always done in buildings, or at least usually have tried to do, although poorly, those are more important. And then on top of that, what can we do? So our very first quiz question, starting off right away. There are 8 quiz questions today. So I'm trying to think of percentage-wise. I think you need to get 5 of them, 5 or 6, whatever it is, to get 70% correct in order to get your PDH certificate. 2 of these are absolute softball questions, meaning there is no right or wrong answer. If you were present and you click on anything, you will be correct. So let me go ahead and launch this very first one. And this one is super easy. Hopefully it popped up on your screen there. Click yes or no if you need us to send you to your email next week a PDH certificate for your PE license renewal. It doesn't matter what you answer. Well, I guess it does. If you answer no, you won't get the certificate no matter how well you did on the quiz questions. But go ahead and answer that for me. Hopefully everybody can see that on the screen. Looks like my other screen, I can see you have it. So answer that as we go here. Why is it not showing up big on mine? It's showing up small for some reason, but that's okay. 88% of the people have answered, so I'll just give it a couple more seconds and let me know if you need a certificate sent to you today. If for some reason you're doing some kind of other CEU thing where it has nothing to do with Illinois and Wisconsin PDH license, but you need a certificate, go ahead and just click yes, and I'll send it to you anyway, and you can do whatever you need to do with it, unrelated to my life. All right, I'm closing this thing. All right, So 81% of you said yes. So we must have a lot of engineers on this call, or people who just like certificates, one or the other. All right, moving on. The other questions will be slightly harder, but they won't be hard. They'll be something we just covered 5 minutes prior. So as long as you're like halfway paying attention, you'll be fine. All right, so let's do the basics. So everybody's on the same page before we start talking about solutions. Indoor air quality. There are, generally speaking, 3 main categories of crap in the air. Particulates, which is, for the most part, just think of it as physical debris, almost visible stuff, some cases even visible stuff. Microbials, which are living organisms. And then, well, microbials are usually living organisms. And then there's gases, right, which is things like carbon dioxide, for example. So those are the kind of things we're going to try to get out of the air, or at least minimize in the air. We'll start off with particulates, right? So this is larger pieces of debris floating around. There are 3 major categories of that. There is dust, which, grossly speaking, is a pretty decent quantity of dead skin cells flaking off people's bodies, plus whatever other crap's in the air. So we have dust. We have dander, which is the stuff shedding off of animals if you have pets, or if it's a pet store or something like that. And then we have pollen, which usually is coming from the outdoor side of the building. But if you have plants inside, you could be generating pollen as well. But normally it's being sucked in from outside because you're not doing a good job filtering that as it comes in. Good job you got fresh air from outside, but you didn't do a good job of getting the pollen out of it. So those are our 3 major categories: dust, dander, and pollen. Largely speaking, people are inhaling quite a bit of that stuff on a daily basis. And normally your nose hair and your lung system end up being the filtration mechanism for those things. Obviously, as we discuss stuff throughout the day today, we'd like to use artificial or mechanical filtration systems to clean up most of that before it even gets to you, right? The second category of things is microbials. Generally speaking, these are living organisms, or very near living. I keep saying it like that because someone's going to argue with me, because they always do. So those also have 3 major categories: bacteria, viruses, and fungus. Bacteria, there is good bacteria and bad bacteria, as most of you probably know. The good bacteria is like the kind of bacteria in your stomach, helping break down food and stuff like that. We're not talking about that. We're not concerned with that. We're more worried about the bacteria in your building that will be causing people to become ill, right? So strep throat, for example, or someone could get a staph infection at a hospital, or E. coli in a kitchen environment, something like that. So we're looking to get rid of some of that stuff out of the space, off of surfaces and out of the air. Then we have viruses. Viruses are technically not living, which is why I corrected myself a minute ago, because viruses cannot survive on their own, at least not for any major amount of time. They need to have a host, so they need to be basically attached to you or an animal in order for them to survive. So they're not technically living, but for the purpose of our discussions today, I'm going to pretend they're living. I'm going to tell you things we can do to kill them, even though they're not living, because it just sounds better to say we're going to kill a virus than it is to inactivate one, which sounds lame. But those are a lot of the things that you are worried about on a normal basis. Obviously, SARS-CoV-2, the COVID-19, obviously is current concern, but we've always had tons of viruses we've been concerned about. Influenza being a major one, the common cold, norovirus like they get on the cruise ships, the original SARS before we had the SARS-CoV-2, right? If you flash back a couple years ago, H1N1, avian bird flu. Every few years there's another virus of the decade type issue, or however long it is. And right now we just happen to have one going on, and people are more concerned about it than in the past. But nonetheless, we're going to try to get rid of those things. And then we have the fungus category, and specifically the type of fungus we're looking to get rid of is mold-based stuff. Just like with bacteria, there is mold that is fine and mold that is harmful. So some mold is fine. You're probably aware that penicillin is a mold-based thing, and it's obviously a medicine that helps people. You probably accidentally have eaten moldy bread before and been totally fine. You don't die from that. Blue cheese has a mold component, right? There's mold that's fine. Then there's also mold that's dangerous to people. And we want to make sure we get that. Most of the mold growing in your building on a wall or surface or something like that is probably not good for you. So we want to get that stuff out of there. And we'll deal with that. This is just the most gross picture that I could Google a couple of years ago on mold. And obviously that's a horrible place for someone to probably be living. That looks like it's probably a house. In order for you to grow mold in a building, doesn't matter if it's a house or a commercial building, you need a minimum of 3 things present. You have to have mold spores. That's easy because there's millions of them floating around in the air, and getting rid of all of them is very difficult. We're going to try, and we'll talk about things today that can help eliminate or reduce mold, but getting rid of all of the mold out of the air is going to be really tough. But you got to have mold spores floating around in the air. You have to have some organic food source for them to eat. And that could be just about anything. They can eat wood. They can obviously eat bread, oranges, bananas, any type of food. They can eat drywall because there's a paper component inside the drywall, so they can eat that up. So pretty much anything they can probably eat. If you really don't want to give them a food source, you got to make your whole building out of like stainless steel, like a prison cell, and then they got nothing to work with there. So you have to have the mold spores, you have to have a food source. Both of those are very difficult to get rid of. And then you have to have a source of water for them. That's the one we're going to focus on because water, believe it or not, is the easiest of those 3 to get rid of. So if you get rid of all the water, then the other ones don't even matter. Sources of water. So obviously in this picture, it looks to me, I don't know if you can get my little laser pointer thing going here. It almost looks, obviously the ceiling's a disaster at this particular building, this house. Obviously total disaster. The walls over here don't look bad at all. They look fine, but it's almost like it's like flowing, right? Almost like it's like a curvature to it. So there's probably some kind of water in this attic, maybe a roof leak or something like that, and the water is finding its way down to the ground, and this happens to be the pathway that it's getting down. If you have things like this, where I have mold here and I don't have mold there, that probably means the water is coming from behind the wall somewhere. Right? In this case, maybe it's a roof leak. If you had mold on all of these walls in its entirety, covering kind of an even pattern, that probably means it's getting the moisture from the air. Why do we care where it's coming from? Well, 1, we can't get rid of the moisture if we don't know the source. And 2, if the moisture is coming from the air, it's an HVAC problem. If the moisture is coming from a roof leak, it's the roofer's problem, right? Or sometimes you might have it in one isolated area, right? And maybe there's a pipe behind that wall, right? Maybe there's a plumbing pipe or a hydronic pipe that has a leak. So you might have just that one, 16-inch wall cavity might have some mold issues. And then you go a couple cavities over and everything's fine. So you got to rip that open and see if there's a pipe leak back there. So for our purposes today, when we're worried about it, we're going to be talking about the mold getting moisture out of the air because that's the HVAC problem, other than a pipe leak, obviously, and what we can do to solve some of that stuff. Obviously, dehumidification is going to be critical. And whatever we do to get rid of this stuff, we have to do it continuously. It's not like we can treat something one time and then walk away. Oh, you got this moldy section of your wall? Let's just take the drywall out, put some new drywall up, and everything's going to be fine. No, it's not going to be fine. 2 or 3 months from now, it's going to be the same problem. The mold's going to start growing on the backside of it, and it's going to make its way through, and it's going to be the same thing. This stuff replicates rather quickly. So whatever we do has to be a continuous thing, whatever our solution is going to be. Our third category of stuff is gases. And that could be tons of different stuff, obviously. But the 2 main things that we're mostly focused on are VOCs, volatile organic compounds. This is pretty much stuff that's off-gassed from all of the things you put into your building. So you buy new chairs for all the employees, they're probably giving out VOCs. Whatever kind of varnish is used on this desk, VOCs. The paint on the wall probably has VOCs on it. You can buy low VOC or no VOC products, like paint, for example, but usually people don't do that, and they have regular stuff, so there is a VOC component to it. When you get a new car, the new car smell, yes, VOCs also. So over time, the VOCs from something will diminish, right? Just like when you get a new car, 6 months later, the new car smell is not as strong. 2 years later, you don't smell it at all because it's almost nothing. It diminishes over time. It has, a half-life type decomposition to it. But when you have new stuff, there's tons of it, and we want to get rid of that quickly. So there are some type of spaces that you'll work in where there's always new ones. For example, I don't know, if you have a furniture store, they're always putting new furniture in there every couple of weeks or every month or 2. There's always new furniture going on display, always new VOCs coming along with that, right? On the example here, there's a nail salon, right? A nail salon, they're obviously constantly painting new nails today and opening more little jars of whatever the nail polish is and the nail remover cleaner and all that stuff. So that kind of stuff needs to be treated constantly. The other category of stuff we get concerned with in most buildings from a gas standpoint is odors. Odors are not generally harmful. They're just objectionable. So if the person in the cubicle next to you has some weird cologne and you hate it, obviously you don't want to smell that. Is it going to kill you to smell their cologne? Probably not, but you just don't want to, right? So odors coming from other people or from things in the building, or maybe you got kitchen odors that are making their way into other spots in the building, or maybe it's an apartment building and the person in the apartment next to you every Wednesday cooks some weird smelling food that you hate, right? Those kind of things we want to deal with. And there's lots of stuff we can do in terms of odor removal, pressurization control, stuff like that that we will talk about. There are other gases that are worrisome beyond VOCs and odors. For example, I mentioned earlier carbon monoxide. That's obviously a gas. Obviously, I don't want it, but I'm not really putting that into the indoor air quality bucket, generally speaking. That's like dangerous, hazardous. These things are not great, right? VOCs might give you a headache. Odors are objectionable, but if you have, a carbon monoxide leak in the heat exchanger of your gas-fired rooftop unit, that's a whole different category of things we got to deal with. All right, our next quiz question. I'm going to populate that here when I get to the button. All right, this is our first real quiz question. All right, which one is not one of the three main pollutant categories that I had just mentioned? Your choices are particulates, gases, mold, and microbial. One of those was not one of the three major ones that I listed up at the beginning. While you guys are answering that, I'm gonna go look at the question. It's gonna be a long morning if I keep getting tongue-tied. Look at the questions you guys type in. So if there's anything you want to ask, go ahead and type it in the question box, and I'll try to address it as we go. Apparently, I made the quiz question harder than I thought. I thought it was super easy, but so far only half the people got it correct. 83% of you answered. I'll give it another 10 seconds. And so far, nobody's typed any questions in for me. If you do, I'll try to pay attention to them and read them. And I am going to go ahead and close this quiz question and share the results with you. I can figure out how to do that button. Maybe. Oh, here we go. All right. So, which was not one of the three main categories of pollutants? The main categories of pollutants were particulates, gases, and microbials. So the correct answer would be mold. Mold would be a subcategory under the microbial. I didn't think I made it hard, but apparently I made it too hard. All right. Try to give you better hints on the next one here. All right, let's keep on moving. Can I not click on there? There we go. All right. So our first category of solutions is going to be related to ventilation, because this has been one we've done for, 100 years, since the plague or whatever. People opening windows as an example. So obviously air quality is a concern. In a lot of buildings, even unrelated to COVID, which has been the past almost 2 years, air quality has been a concern. Inside buildings and inside homes, the outdoor air level is significantly better than the indoor air level. Almost everywhere in the whole country, the outdoor air is cleaner than the indoor air. There's exceptions to that, like there's always exceptions. If you live next to some kind of, coal-fired power plant or something, obviously that's different. But in general, if you can get the inside air to the outdoors and bring the outdoor air in, you're going to be much better off in your building or your home or whatever. As buildings get tighter and tighter, it becomes more and more critical that we have mechanical ventilation systems. If it's an old, crappy, leaky building, you're accidentally ventilating it through the leakage. But as you tighten up old buildings, or as you build new buildings which are inherently tight, that becomes more problematic, both from a humidity control standpoint and as well as trapping all the VOCs from the furnishings in the building. So we got to pay more attention to that. Residentially, if you look at any of our energy codes, there is leakage requirements for how tight the building needs to be. And because of that, they're doing blower door tests to make sure the building's not leaky. Because of that, residential buildings now require mechanical ventilation. Commercial buildings have required mechanical ventilation for decades, so we were already there on that part of the equation. To make sure everyone's on the same page as me, I want to make sure that we separate these things from the mechanical ventilation we're about to talk about. So these are things that also bring air in and out of a building, but they do not count as my mechanical code required ventilation air. So if you have gas-fired things in the building, normally furnaces and boilers, but also water heaters, kitchen ranges, stuff like that, if you're going to be having these type of appliances exhaust air out, you have to have air coming in somehow. In an old leaky building, it wasn't a huge deal because it would just suck it in the cracks. If you turn something on, like for example, at your house, you turn on your range hood and you're sucking 100 CFM out of your kitchen, right? It would just leak in somewhere else, right? Same thing that happens in commercial buildings, right? The boiler, if it's relatively small, the boiler would just suck air from the building and the building would be leaky enough that would kind of work out and you'd get enough combustion air coming in. But then as boilers get bigger and bigger and the boiler room gets bigger and bigger, now you have to put combustion louvers in the wall to open up whenever the boiler's on to be able to suck enough outside air in. Or you got to go to direct vented appliances. So anytime you have combustion going on, you need to have a pathway for air to get into the building, into the area of the mechanical equipment in order for that guy to use that air for combustion and exhaust it out. That is not part of the ventilation air we're talking about. If you need to bring 500 CFM in for some big giant boiler, that's fine. You got to do that. It doesn't count towards your ventilation requirements that I'm about to explain. Additionally, there are some areas of the building that I want to intentionally exhaust from, not combustion related, but just other reasons, typically odor reasons, like a bathroom, right? If I recirculate air from your bathroom into your office area, your building, it's not going to hurt anybody. But nobody wants to smell that, right? It's not a good idea. So we put exhaust fans in bathrooms. They're code required. They're smart to have. You got a little individual bathroom. It's got whatever, 100 CFM bath fan in it. I have to have a way for air to get back into that building somehow, right? But in any case, any of these exhaust sources are not going to count towards my ventilation incoming air requirement. So what is that requirement? There are different places to get that number, to figure that out. So normally, for most of us, with the exception of the city of Chicago, which is its own little bubble of the world, and the state of Wisconsin, which is also in its own bubble of the world, everywhere else that I can tell is using ASHRAE 62.1 or IMC, International Mechanical Code, but it's the same table. IMC literally cuts and pastes the ASHRAE table into their document. There's other stuff in the document that changes, but the ventilation table, I've never seen it not be identical. So this is just showing you one page of that table amongst the 3 or 4 pages that is there. And this is how you would use that table. So you'd pull up the section you want. I'm going to do, for my example, an office building because it's a pretty normal, common scenario, right? So I got an office building right here, office spaces. There's a bunch of numbers on here. Some of them I can ignore right off the bat. For one, I don't care about liters per second because I'm in the US. So 2 of those columns just drop off. And now I have 2 columns left over here. I have CFM per person and I have CFM per square foot. And I need to add those 2 numbers together. So if I have an office building, it's 5 CFM per person. Why is this not? What's going on here? My mouse is not playing it. I have 5 CFM per person, right, down over here. And then I also have 0.06 CFM per square foot. And I add those 2 numbers together. So I'll do an easy example. If I have 100 people, right, obviously I need 5 CFM per person. I need 500 CFM of outside air. But let's say it's also 10,000 square feet. My handwriting is just as bad in real life as it is on the computer. And I need 0.06 CFM. That is 600 CFM that I need. And I add those 2 numbers together, 500 plus 600. I need 1,100 CFM for this fake space that I just made up, this office building. If it wasn't an office building and it was a classroom at a school, then instead of 5, I would need 10. Instead of 0.06, I would need 0.12. So for the exact same size space and same number of people, I would need 2,200 CFM if it was a classroom versus an office building. And then if it was a little kid classroom, I would need even more. I don't know why that is. I assume it's because kids in a daycare are like licking toys and handing them to each other or something. So there's more concern. I don't know. So the kind of space will dictate which one you're in. And like I said, there's like 3 pages of this. You find the general type of building you have, and then you find your space within there the best that you can. If I happen to have offices at my school building, I'm going to go to education. There's not going to be any offices on there, but it's basically an office building attached to the school, right? So I would know for the office area, the principal, vice principal, dean, all that stuff. This is the category I'm in down here, 5 plus 0.06. The reason why we have 2 numbers, it used to be just 1 number until maybe like, I want to say 2004 for ASHRAE and 2006 for IMC. We used to have 1 blended number, but now we have the 2 separate numbers. And the entire reason for that is to separate them so I can control them differently. We talk about demand control ventilation in a little bit. What I'm going to be allowed to do is modulate this 5 CFM per person portion if everybody doesn't show up to the building. But I can't modulate the 0.06 CFM portion because that's to take care of the building itself, the off-gassing of the paint and the furnishings and so forth. That doesn't change if I have 1 or 50 people there, but the number of people needing fresh air does. Because the 2 main pollutants in my building are going to be people. You're coming in with your body odor and your germs and your whatever. So I got to get rid of your stuff, and then the building itself. So I can modulate the people portion, not the square footage portion. So hopefully that makes sense. If it does not, type a question in. If you are in the state of Wisconsin, which I know a couple of you guys were when you registered, this whole table doesn't apply to you. In Wisconsin, no matter what, it's 7.5 CFM per person, and that's it. Nothing else. There's no square footage portion. It's just 7.5 CFM per person. It's like the least ventilated state there is. I don't know why, just that's the way they do it. The city of Chicago is actually the most ventilated code I can find in the country. And the city of Chicago is also weird. They do not give you a table like this at all. What the city of Chicago says is you have to have 33% of your supply air has to come from the outdoors, meaning you can recirculate 67%. So that's how they do it, 33%. Chicago does have a table like this, but it's not for ventilation air. It's actually for supply air, which is completely weird because, as most of you guys know, because you're engineers, the supply air CFM should be dictated by my load, not my square footage. I might have a square footage of a certain space that has single pane, crappy, leaky windows. I might have another one that's a super tight box. Should not be the same answer. But in Chicago, the amount of CFM you deliver to a space, supply CFM, is based on the square footage, not the load. And then the outdoor air fraction is 1/3 of that, which ends up being a very high amount of outside air. So Chicago is the most ventilated. Wisconsin's the least ventilated. Everywhere else is what I would call normal. I apologize if you are an official in Wisconsin or Chicago and I just made fun of your code, but you need to fix it. All right. With COVID, a lot of the suggestion was to overventilate, like double all your outside air rates. This was in mid-2020, like May, June, those kind of recommendations were coming out. They were pretty short-lived because for many reasons they don't work well. So this example here, let me switch to a little laser pointer thing maybe. This example here is showing you a couple different modes. I have heating, economizer mode, mechanical cooling, and then I have integrated economizer mode here. For this particular example, it was a 40% outside air ventilation rate, which is actually really high, but that was the example on here. So at all times, you can see I'm bringing at least the code required amount of air in, 40%. By the way, I should also mention that these amounts in here are only when the building is occupied. If the building is unoccupied, you do not have to ventilate it. You are not required by anyone's code to ventilate an unoccupied building. And in fact, most energy codes require you to stop ventilating an unoccupied building, right? So if you have an office building, it's open from 6 a.m. to 6 p.m. At 6 p.m., you shut the ventilation system off. If you got 2 people in there cleaning, it doesn't count. They don't count against that. It's still unoccupied. There's enough volume of air that we have enough dilution for those 2 people because the other 100 people are not there. But you don't have to ventilate in the unoccupied hours. So this chart doesn't even show that. This is assuming occupied hours. Recommendations from some people, bad recommendations, i.e. CDC, which I don't want to pick on the CDC, but they've recommended a lot of bad things during COVID. Not necessarily because they did something wrong. It's just they're reacting so quickly that didn't think it all through. But in any case, they were telling you double your ventilation rates. So in this example, it would have went from 40 to 80%, right? And in heating mode, what that would mean for me is, A, I'm spending a lot of energy to heat all that outside air. And I think everybody knew that was going to happen, and they were okay with that. Like, hey, let's waste some energy, if you will, in order to keep people safe while we figure out what the hell is going on. All right, that's fine. If I'm in mechanical cooling mode and I do that, though, it gets kind of detrimental on the dehumidification side, which I'll show you in a second. And if I'm in one of the economizer modes, I'm already overventilating, and that's okay because I'm at a more mild temperature, say 50 to 70 degrees outside, so I don't have an energy penalty. In fact, it's an energy benefit to overventilate at that point in time. I don't have a humidification concern as long as I have an enthalpy-controlled economizer. So I'm okay bringing more outside air in during those moments. But mechanical cooling was a detriment. So this is actually from some real building. I forget which one it was on this CDC report, but they were at whatever normal ventilations day. This is right when COVID was starting to happen, like, you know, that mid-March when the, you know, crap hit the fan kind of thing, right? They're at normal ventilation rates, and then if the building closed for a few weeks or whatever, decided to reopen, started following the new, at the time, CDC guidelines to double your ventilation rate, and you can see what spiked up on their return air relative humidity readings, right? They had this huge spike in relative humidity. Instead of being way down here in May when they were like 35, 40%, now all of a sudden they're at 55, 60, in some moments 70, 75% relative humidity, which is going to be a problem. The higher the relative humidity is, the easier it is going to be for mold spores to pull the moisture out of the air and use that. So I don't need a roof leak or a pipe leak in order to grow mold. I can just pull the moisture out of the air. If I can keep things in check, specifically as far as ASHRAE standard 62.1 is concerned, which is the indoor air quality standard for the country, I need to be below 65% to minimize my chances of mold growth. If I start getting higher than that, and I forget what somebody told me, I don't know if this is true or not, but enough people have told it to me that it's kind of like a wives' tale, and I sort of believe it. At 70% relative humidity, it'll take about 2 weeks to grow mold, and at 80% relative humidity, it takes about 3 days to grow mold. You keep stuff under 65%, minimal mold growth available. We do have 2 ASHRAE standards that dictate relative humidity recommendations. The indoor air quality standard, as I mentioned, which is 62.1, the recommendation is 65% and below. And then we also have ASHRAE standard 55, which is the standard for human thermal comfort. And that standard recommends you keep it below 60% for human comfort. So when somebody asks me what they should be doing, and I know one standard is 65 and one says keep it below 60, I just tell them keep it below 60 because if I'm below 60, I'm obviously below 65. And personally, I like to control spaces, which we'll talk about, to 55% humidity because most of the controls let the humidity float 5%, so it'll float up to 60, and then my system will drive it back down to 55. And then the sensor will let it float up to 60, and I'll drive it back down to 55. So my control set point ends up being 55 in a lot of cases. Or if you've been to any of my like residential smart thermostat classes or anything like that, you'll know that I control to 54%. Because for some reason in those thermostats, they only have even number set points allowed. So my choices are 54 or 56. So I just set them for 54. They float up to 59. They run the dehum mode, get me back down to 54, float up to 59, run the dehum, and so on. Keeping people comfortable is important. If people are not comfortable, they waste time finding ways to be comfortable. There's so many different statistics that I could show you. I have a whole nother older presentation that has like 5 slides of statistics. But the cost of people in a building is significantly higher than the cost of energy. The cost of energy is nothing compared to the people. Right, and they're showing you down here, if it costs you $100 a day for your gas, electric, and water to operate your building, actually all of your operating costs, not just gas, electric, and water, but everything, maintenance, security guard at the door, that kind of stuff, versus the cost of the salary of all the people that work there, it's a magnitude of 10. So if you do things to penny pinch and save energy, or worse, you do things to build the building cheaper to save first cost, that are then much harder to fix later, more expensive to fix later, you're doing it at the cost of the people. So for example, you size the equipment wrong, you don't put enough staging in, whatever it is, and now you can't really dehumidify well, people will find ways to dehumidify. They'll jack the thermostat down to 68 degrees to get the cooling to run longer to dehumidify. which is obviously extremely wasteful from an energy standpoint. But that's what they're going to do. You've all seen people take combinations of little paper clips and put them behind the lock boxes of thermostats to kind of try to fake the set point out, or they hold lighters under thermostats. They do weird stuff that's a waste of time in order to get things comfortable in there. Some of you probably heard me tell this story before, but I went into one of our buildings. This is probably almost 10 years ago now, and one of our facility dudes was standing on a ladder with a cup of water, a styrofoam cup of water, with some wires into the cup, right above someone's desk. I'm like, dude, what are you doing? It's like, well, there's this duct sensor in the duct that keeps tripping out the unit. So then the heat doesn't run and the space gets cold for a while before it kicks back on. So I found if I hold it in this cup of ice water, hold the sensor in there, it keeps the system running. I'm like, dude, how long do you plan on standing on that ladder? I don't know. I'm like, dude, this is completely unproductive. Like, why don't we figure out why the duct's so damn hot to begin with? Yeah, I guess we could do that. Like, this dude was planning on standing there for God knows how long, an hour, a day, I don't know. Wasting time, stuff like that. So people find a way to get comfortable. They put space heaters under their desks. They jack thermostat set points down to really cold temps to dehumidify. So whatever we do to save energy in a building, it should not be at the cost of safety or comfort, right? Those are the priorities: safety, comfort, then energy, right? So let's see if anybody has any questions. I don't see any questions typed in at the moment. If you have anything, just type them in that question chat box, and I will do my best to answer those. So let's talk a little bit about demand control ventilation, because we're on the ventilation topic, and I was just talking about energy, so it kind of ties in. So we'll do demand control ventilation, and then we'll move over to filtration and purification stuff. So CO2-based demand control ventilation, it's a solution that people have had for a couple decades. We started doing it at our office, I want to say in 1999. I mean, I guess it could have been earlier than that somebody did it. I didn't know about it. I started here in 97, and the first one I did was 99. But it's very, very common now. Every building automation manufacturer does it nowadays. It's super common. And it doesn't not make the air cleaner. We kind of lump it in the indoor air quality stuff, but it really has nothing to do with indoor air. It has minimal to do with indoor air quality. But it's mainly an energy saving thing. But the idea is to save energy without sacrificing indoor air quality. That's kind of the combo here. So this is kind of the crossroads of those two things. Got all these standards that want you to have fresh air. Got these other standards that want you to save energy, and they're crisscrossing. Where's that middle point that I can do both of those things? This kind of helps me do that. So we're going to make sure that we're looking at temperature. Ideally, I should add humidity to this. Temperature, humidity, and ventilation. If I get those three right, that's like the trio of magic that can happen. The way we ventilate buildings normally, historically, has been the same way we've always done it, which is we look at those tables I showed you, or older versions of those tables, and we just add up how much we need. So this chart is off of office buildings. You can make a similar chart for other types of buildings as well, but it would look similar, just different numbers on the side column over here. But what this guy is showing me is that I got these different ventilation rates. In this case, the old standard per person, right? And you can kind of almost ignore the giant pyramid, even though it's the most visual thing on here, because if you're working in a building that has not been updated since 1914, we've got a whole bunch of other problems going on with your project. But anything that's post-World War II built or rehabbed, which is pretty much everything at this point, you're on one of these other ventilation rates. So we had 10 CFM per person for a very long time. After the 1970s energy embargo crisis deal, ASHRAE cut that number down to 5 instead of 10, cut it in half to save energy. That was short-lived because 5 CFM per person does not get the job done. And by the way, this is 5 CFM total per person. Whereas before, when I was talking about 5 CFM, it was 5 CFM plus 0.06 CFM per square foot. The old standard was just the per person thing. That was it. Not enough ventilation air. So that caused some of the sick building syndrome problems we had for a while in the 80s. So ASHRAE overreacted and went the other way and went to 15 CFM per person, and then eventually up to 20 CFM per person. And now, for the past 17 years at ASHRAE, and the International Mechanical Code follows that, we're at approximately 17 CFM per person. I say approximately because 2004 is when we stopped the per person number, which is why this chart hasn't been updated really since then, and my general laziness. we stopped the per person and we went to the per person plus per square foot. So for a typical density of an office space, it averaged out to about 17. So this is a retail space. So retail is not 5 plus 0.06. Retail is 7.5 plus 0.06. So this is a bank, so it's retail, right? So for this space, if we designed it for 25 people, we needed 480 CFM of fresh air coming into that building at all times, right? And then if for some reason, at the end of the day, there's only 5 people there, we'd still bring in the 480. And if that lady was by herself, counting some money, still would bring in 480. That's the way we would have always done it. And in fact, more than half of your buildings are still designed that way. Bring in a fixed amount, and that's it. So the goal of demand ventilation is to get the right amount of air to the right spot at the time that we need it there. All right, so the reason we're doing this, like I said, is the crossroads of those ASHRAE standards or their associated mechanical and energy codes. When, hey, one says don't waste any energy doing stupid stuff, the other one says bring in a bunch of fresh air to help people. All right, so we're going to do both of those. We're going to use CO2 measurement for our demand control ventilation. It doesn't have to be CO2, but it almost always will, because that's going to allow me to track people. If my pollutant problem in the space is people, which it usually is, especially for offices, school, retail, if I know how many people are in the room, I can decrease the amount of ventilation when less people are there. If I designed it for 100 people and I only have 10 there, I can throttle that number down to a lower amount. The way we determine how many people are there is CO2, because people exhale CO2. You suck oxygen in, you exhale CO2. If I measure the CO2 in a room, it's kind of a surrogate way of me counting how many people are actually there. You should know that CO2 is not considered a pollutant. It is not harmful. I mean, it's coming out of your face. You're the one putting it in there. Now, if you get to really, really high quantities, yes, it can be a problem, mainly because you're not getting as much oxygen as your body would need to optimally perform. So yeah, it could be a problem in that case. But for normal levels in a building, right, 800, 1200, 1500, no one's going to die because you have 1500 parts per million. Hell, no one's going to die if you have 3000 parts per million, but you're not going to be fully functioning in an awesome way. So there's going to be an optimal place we want to be. But just know it's not a pollutant. It is also not carbon monoxide. Yes, it has a C, and yes, it has an O in the name. That's it. They both have a carbon, and they both have an oxygen. But CO2, 2 oxygens, is completely different gas than CO, carbon monoxide. I say this because I can't tell you how many sets of blueprints I look at that call for carbon monoxide detectors in an office building. And I'm like, but you guys have a heat pump with electric heat. You don't even have anything doing combustion. Why is there a carbon monoxide detector? Like, we want to do that ventilation thing you talked about. Well, time out. You meant CO2. That little 2 is important on there. It's a big difference on there. So normal levels in an indoor space, they're showing you here down to 400. That would be like if you're in full economizer mode and you're bringing 100% outside air in. Then maybe you're down at that level. But normally you're going to be like 800, 1,000, 1,100, 1,200, 900, something like that. If you're up in this category, 2,000, 2,500, you're doing a really crappy job of ventilating. We should be more like nearish 1,000. We'll talk about set points in a minute. We should be near 1,000. That's kind of a place to remember. Outdoor levels are very constant. If you take an outside air reading today and you take one tomorrow and next week and next month, they're all going to be pretty close to each other. Like around here, where I'm in North Aurora today, and when I go outside and take readings out there, it's usually like 420, 440, 450, 430, something like that. Low 400s is pretty normal. When I've taken them outdoors in downtown Chicago, I'm usually high 400s, 480, 500, 490, something like that. The levels stay pretty constant, day over day, month over month, year over year, right? So what that means is if I know the outdoor level of CO2, and I know the indoor level of CO2, that differential, that can help me basically calculate how much ventilation air I'm bringing in. And the amount of people breathing in there means I need more ventilation air. And the less people breathing in this space means I need less ventilation air. So it kind of tracks up and down together. People and CO2 work nicely like that. So like I said, you're exhaling CO2. It's coming out of your mouth. It comes out of your mouth at a very predictable rate based on what you're doing, your activity level. The more you breathe, the more CO2 you produce. The more work your body's doing, the more you must consume oxygen and exhale CO2, right? So if you're on the treadmill, you're somewhere over here. You're at 4 times your 4 times the metabolic rate of someone who's dead, basically, or almost dead. Let's just say you're 4 times the rate of somebody who's sedentary, right? You're over here, you're producing significantly more oxygen and hence CO2 production. But if I go from 1 to 4 here, I actually go from approximately 0.25 to 1 there. This is a 45-degree line almost. So it's pretty much a 1-to-1 relationship. If you double the amount of activity level in your life, you double the amount of CO2 production. If you triple it, you triple the amount of CO2. If you quadruple it, you quadruple the amount of CO2. For a lot of spaces, we don't really consider the activity level, right? Because a lot of stuff that we do is offices or light stuff or just, a little bit of walking, like around a store or something like that. But if you were doing like a fitness center or something, then maybe you would, think about it a little bit differently. But it's still going to be a pretty linear relationship, so I'm in pretty good shape there. If I take the amount of people in a space and I double the amount of people, it's going to double the CO2 production. If I quadruple the amount of people, it quadruples the CO2 production. That's why we can use it to track our ventilation rate. I don't really care how much CO2 is in the space. It's not harmful. It's not bad for you. I don't really care. I'm just using the CO2 to count how many people are there. And if I know how many people are there, I know how much bad stuff they're giving off. Germs, cough, weird, funky perfume, whatever it is. All right. So I'm really wanting to track people to get rid of people pollutants, and CO2 is my way to count the people. In a given space, depending on my ventilation rate, it'll take a certain amount of time for a room to settle out. Now, these per person numbers over here, these are blended rates. So it's per person per square foot, basically the old standard, if you will, right? So an old building, if I needed 15 or 20 CFM per person blended people and square footage, I'd be on the yellow or green line over here. This is hours, right? So if I looked at those guys, you could say after, say, like, 30, 45 minutes at one of those ventilation rates, I'm pretty well leveled off. It's pretty constant. If I had a really low ventilation rate, like only 5 CFM per person total and nothing per the square footage, it would take me 2.5, 3 hours to kind of level off. The higher the ventilation rate, the faster things average out in the space, which kind of makes sense, I guess. However, when I put a CO2 sensor on the wall in the room to measure what's going on in there, that doesn't mean the CO2 sensor waits until things level off and then I react. Everybody piles into the conference room. The CO2 level is going to start going up. I don't wait till it gets to a really high emergency point and then do something. As I see it creeping up, I start opening the ventilation more. And then later on, people are leaving the conference room and I see the CO2 level dropping down. I start closing the ventilation rate back. It happens in real time. It's not an open closed damper. It modulates based on how much CO2 is in the space. So in real life, what's this going to start looking like? That same little bank job with the same lady working there with the same customers. I'm bringing in the 480 CFM of outside air. If only 5 people are there, I can throttle it back down to 340 CFM. And if she's by herself, I can throttle it back to 308. So 308 is still a lot of CFM, and it didn't go down as much as you might have thought because I still have the square footage number. That number doesn't change. That's a constant. So I don't remember what square footage this was based on, but whatever square footage that was based on, that was 300 CFM. And then I had 7.5 CFM for that one lady. That's how I got to the 308 on this calculation, right? So this was also based on 300 CFM, right? But then 7.5 times 25 people was 187.5. That's how I got to the 488. So I modulate the people part, not the square footage part. The square footage doesn't change. The amount of couches off-gassing doesn't change, right? The amount of varnish on that counter doesn't change. If you have a zone system, we can still do this kind of technology. But instead of having one CO2 sensor modulating my outdoor air damper, each CO2 sensor is going to modulate its zone damper. So now my zone is being controlled not only for temperature to cool as much as I need to cool in the VAV system, but it also can have a CO2 sensor overriding that. So if the conference room starts filling up with more people, the CO2 sensor will ask for more air into that room, which means that it's going to take more air out of this duct. And then the damper up in the air handler, what that guy does is he looks at all 1, 2, 3, 4, 5, 6, 7, all 8 of these zones. He looks at the worst one, who's farthest from their CO2 set point, and he controls his damper to that. If I can get enough air in this conference room up here to satisfy him, the worst zone, the one farthest from his set point, everybody else is going to get enough air. They're going to get more, actually. Now, when I say it like that, it sounds wasteful because I kind of said it backwards. It doesn't really work like that. I don't bring in more outside air when more people come into the conference rooms. I mean, I do, but in reality, I design every room for the maximum occupancy, and I design the zone for that, and I design the outdoor air damper for that. And what really happens, and what I want you to think of, is as people leave those rooms, I throttle the ventilation back. If they come back into the room, I go back to what the ventilation and cooling rates would have been to begin with. So I don't have this concern with overcooling the space, because I would have always been overcooling the space if that was my problem, right? If this room is designed for 15 people, I designed everything for 15 people as if I did not have any CO2 sensors at all. And then I add a CO2 sensor on the wall, and when less people show up, I can throttle the damper back some. So don't think of it, and the same thing works on single zone. When you have one CO2 sensor controlling the main outside damper, don't think of it as it making the damper go more open. It doesn't do that. Think of it as starting at the code required CFM, and it actually goes below that when less people show up. The mechanical and energy codes allow me to do that. Go below the code required ventilation rate when less people are there, as long as I have a way to know that less people are actually there. So that's been allowed by the mechanical codes. It's in ASHRAE 62.1, which, as you know, feeds in the mechanical code, and it feeds into most local codes, with the exception of Wisconsin and Chicago. Everywhere else pretty much follows this. It's been in the code in the standard, ASHRAE standard, since 2004. This is the language on the 2013 version, but it's the same language as 2000 and what would be 2019 we're on currently, where I'm allowed to do the CO2-based demand control ventilation. You could also make an argument to do it by something else if you have something else to look at, right? Maybe you want to do, maybe it's a classroom and you don't really want to just ventilate for a certain number of kids. You just want to know if the kids are in the room or not in the room. If they're in the room, ventilate fully. If they're not in the room, throttle it back, right? So maybe you put a motion sensor in, right? You could do it that way. Most of the time we use a CO2 sensor, but if you're putting motion sensor in anyway for, say, lighting, same sensor could have two contacts and do double duty. It's not as accurate as CO2, or I shouldn't say not as accurate. It doesn't modulate like CO2. So I don't get the benefit of the little parts. For example, if your classroom is designed for 25 kids and there's only 20 there, CO2 would save me 5 kids worth of outside air. Motion sensor would not. It only would help me on the moments when the kids all leave. If you are in the city of Chicago, demand control ventilation is even more important there than anywhere else in the country, because they already have a really high ventilation rate. So if I can get that thing throttled back, the savings is greater. Wisconsin is the least exciting place to do it from a financial standpoint, because they have the lowest ventilation rate in the country. So I'm only able to go from here down to there in Wisconsin, where Chicago I can go much further down. But Chicago's had this in the ventilation code before any of the national standards had it. This is like the one time the Chicago code was like ahead of the curve, if you will. The only thing weird about the Chicago code is they actually specify a specific CO2 parts per million set point that you must use of 1,000. Pretty much everywhere else, we're doing 700 parts per million above the outdoor air level. And so that means if your outdoor air level is 400, your set point becomes 1,100. If your outdoor level is 450, your set point's 1,150. That's the normal way we would do it. But Chicago's a little more conservative, probably because they were the first ones to add it into their code. So I need 1,000 parts per million set point. But nonetheless, at least I'm allowed to do it. So not only are the mechanical codes requiring this, or allowing this, I should say, but some of the energy codes, actually all of the energy codes now, are requiring this. So anybody who has an energy code that is newer than 10 years has this in there by code. So in some places, like I think Indiana might not be updated yet. I think Indiana might still be on the 2007 standard. Tom, I see your question about calibration and sensor life. I'm going to address that in about 5 minutes, so I'll get you there in a second, Tom. See, I can read at the same time that I'm speaking to a degree. So sometimes required by energy codes. It's required in 90.1, which, as you know, feeds into the international code, which feeds into most of the local codes, including the entire state of Illinois, including Chicago, and including the entire state of Wisconsin. So even though Wisconsin and Chicago have unique requirements on their mechanical code, their energy codes are in sync with this. And this is the language from the energy code. On the current codes, if you have a occupant density ratio of more than 25 people for every 1,000 square feet, you're required to do demand control ventilation. This has been in the code for 10 years now. and the ASHRAE standard longer than that even. There are some exceptions to that, right? There's some spaces down there. If you got some really small spaces, okay, you don't have to do it. If you're doing energy recovery already, you don't have to do it because you have a different way to save a bunch of energy on ventilation. So you're doing something different than that. If you got an old pneumatic VAV system, you get an exception because with pneumatics, you can't do anything fun. So they know that already. I apologize to anyone who loves pneumatics. So there's some exceptions there, but in general, 25 people per 1,000 square foot density. What does that mean? That means classrooms, movie theaters, conference rooms. If you have offices with really small cubicle area, like you have a bunch of these 6x8 little cubicles for like a call center or something, you probably have the density where you're going to have to do it. You have something bigger with giant private offices where each person has their own, 15 by 15 office. You're not going to have to do it. All right, so we're going to try to get the actual ventilation rate for the amount of people that are actually there, which saves me on the over-ventilating. It's a pretty good payback scenario. And what it doesn't say on this slide is it actually is a nice way, if you're doing it on a building automation system, it's a nice way to illustrate you ventilated correctly if you ever had to prove that. If someone said, yeah, the reason my guy got sick is because you didn't ventilate the building correctly. You can show the ventilation rate history off the building automation system because you're tracking it now. And you're using CO2 as your kind of measurement for your ventilation rate. So you would have a way to prove that out. So what does it look like when I put it in an actual building? This is an actual building. This one, sadly, my graphic is from the 90s at this point because I'm old and I haven't updated anything. But it's an actual building. This orange bar on the bottom here is showing my base ventilation rate. This is going from midnight to midnight. In reality, during the unoccupied hours, it actually goes to full ventilation. This is 100% ventilation, not 100% of damper travel. That would be way up here. 100% of my ventilation rate required by code. But in the unoccupied hours, the damper goes open when I turn the heating and cooling on, and then all the way closed, and then open, closed, open, closed. And for this building, it averaged out to like 29% or something. So instead of showing this sawtooth pattern on the graph, they kind of just averaged it right here. In reality, if the building's unoccupied, you should be shutting your damper. But a lot of buildings don't actually do that, so you get this effect. In any case, this building went occupied at 7 a.m., looks like, all right? And then a normal scenario, without demand ventilation, it would go to its ventilation rate. It would sit there all day long until, 7 p.m., and then it would go back off. And everything in the green is the amount of ventilation that would provide. When you add the CO2 sensor demand control ventilation to this, you get the purple outcome of what's actually going to be needed for ventilation. So in other words, everybody doesn't show up to work on time. Some people are sick. Some people got a field visit to go to. Some people just show up late because that's what they do, right? And then by 9 o'clock, most of them are there. Some of them cut out early for lunch. Some of them eat lunch in the building. Some of them eat lunch out of the building. Most of them come back. Some of them don't bother, right? And then people cut out early and they go golfing and whatnot. You end up getting this pattern here. Every office building in America gets this two-hump profile. There's numerous studies showing that. This two-hump profile for offices. If you work in an office, there's only 2 people that work there, okay, maybe you don't get that pattern. But if you get an appreciable amount of people, you always get this pattern. Restaurants always get a 3-hump profile. There's very predictable profiles we can look at and utilize those to estimate energy savings. To give you some examples, this is real projects but kind of averaged out. Here's some office projects here in the first one showing, I'm going to call that 28% reduction in energy on average by just tracking the people not being there. Basically, during the daytime, it's 28% unoccupied on average. That means sometimes it's half unoccupied, other times it's 98% occupied. But 28% reduction in outdoor air needed that I don't have to heat, cool, filter, and ventilate. Retail, it's like, I don't know what that is, 91% reduction, huge reduction. Because retail is designed for some peak crowd of people that hardly ever happens. It's like a Black Friday type crowd or something like that. It hardly ever happens. So I'm always way down here. Restaurants, same kind of thing. It's like an 88% reduction or something because they're designed for some kind of Saturday night dinner crowd. But Tuesday at 10:30 in the morning, it's not that busy there, right? And then schools, it's 71, 72% reduction. I'm trying to eyeball it on this graph without having my notes in front of me, which is dumb. But you got this reduction here. Schools, it comes from multiple things. One, you're not fully occupied in the summer. You have very partial occupancy. You get a lot of savings there, right? 2, like I said before, sometimes there's not anyone in your classroom. When your kid goes to PE, his classroom is probably empty. There's nobody there. Why am I ventilating it, or why am I fully ventilating it? Throttle that thing back, right? as the kids move around the building, every room they go into was designed for peak ventilation rate, but they can't be in more than one room at a time. So there's times when there's no one in the gym. There's times when there's no one in the cafeteria. There's times when there's no one in the art room, right? So those rooms can be all throttled back. And then the other thing is that you might have rooms that are designed for 25 kids and you only have 21 in the class that year. That's 4 kids that you don't have to ventilate for the whole year long. So you add those things up and it ends up being pretty appreciable. Those are just some examples of paybacks around the country, just examples. We could do real calculations on real projects. Sometimes the payback is like 2 months. Sometimes it's like 2 years, depending on how much ventilation area you're working with and whether you're in Wisconsin or not. Paybacks are bad in Wisconsin. Not bad, but they're longer. They're more on the 2-year range. All right, so if you're doing a project, you got to figure out if this is going to make sense for you. There are things you have to pay attention to other than just the people. For example, if you have a lot of outside air intake because you need to pressurize the building because you have a lot of exhaust fans, like in a laboratory or something, this might not be the best thing for you, right? Because you can never go below a certain amount of outside air when you have a lot of exhaust fans running. So pay attention to those kind of requirements and things that are going on in the space. This chart is literally, I was going to say older than me. It's not older than me, but it's older than when I started working here in the 90s. And it pretty much is almost still current, almost. So on this chart, we used to give this to our sales guys. Probably should do the same thing again. A meant it was a good application, right? No problem with doing it. C meant it was a horrific idea. Don't do it. Someone's probably going to die. Don't do it. B meant come talk to me. I need some more details, buddy. What are you thinking about here? Right. So A's, classrooms, music rooms, auditoriums, theaters, any type of indoor sporting venue. I mean, you got the college basketball Division III team, which is mediocre. The space is designed for 4,000 spectators, but because they're mediocre, it's like 400. Right? I can cut back that ventilation rate. I don't need to ventilate it a lot. Office buildings, most retail spaces. If you're at a hospital, we tend to not mess with stuff at a hospital. There's all kinds of pressurization rules, but I have like lobbies and waiting areas and corridors and stuff like that I can do it. Hotels, there's a lot of spaces I can do in a hotel. It's not going to be the living areas, the sleeping areas, because there's like 1 or 2 people in those rooms. That's not enough to do it. But the conference areas and the meeting rooms and the ballrooms and all that stuff, it's a great idea to do it. Movie theaters, stuff like that. Bad ones are either ones where the population, the people amount doesn't really change, or there's some kind of weird chemical thing going on, right? So dry cleaner. The ventilation rate in a dry cleaner is dictated by the cleaning chemicals. I'm not messing with that. Locker rooms, they already smell bad. I'm not messing with that. Pet shops smell bad, not messing with that. You can do demand ventilation in kitchens. It's just a different type of system. It's not CO2 based. Pretty much you're counting how many burners are on and adjusting your exhaust fan based on that. Different conversation. And you can also do it in parking garages, but also not CO2 based. And there you'll do it carbon monoxide because that's what your car is exhaling. Or you'll do carbon or nitrogen dioxide because that's what diesel vehicles are putting out. But it would not be CO2. That's why it's a no. Other no's, warehouses, they're too big and not enough people in there. Like the cubic volume per person ratio is such that I can't even count people with a CO2 sensor. It's too much air. Autopsy rooms and mortuaries, people are dead, they're not breathing. Swimming pools, chlorine is my problem, not the people, right? And then the maybes, we just got to ask questions on. Like any of these ones here, they might have weird chemicals going on, right? Like a nail salon. So I got to think about those and how you're ventilating it. And I might say yes, I might say no, depending on what you're doing there, right? For example, the nail salon thing. Some of the higher end nail salons have an exhaust fan right at the technician station. So they're exhausting directly off of your hands. In those cases, I could mess around with the ventilation rate in the main space. But in a lot of places, they don't have that exhaust fan. They have a general exhaust for the whole room. In that case, I'm not effing around with the makeup air coming in, right? So those are some things to think about when we're controlling these things. All right, I gotta get my coffee in there. I'm going to have to pick some base ventilation rate. I used to have to guess at this. It was totally a guess. And I'd always end up with like 20, 30, 35%, depending on what I was basing it off of, usually pressurization reasons. Then when ASHRAE standard 62.1 got modified in 2004, and hence the mechanical code in 2006, They gave me the base ventilation rate. That's the whole entire reason they separated the blended per person number into a per person plus per square foot number. The square foot number became my base ventilation rate. And then my total number was the base ventilation, square footage, plus per person. And they essentially said you can modulate between these two numbers. That is the only reason we separated in the ASHRAE standard, to make you do math, because that's fun, and then to allow demand ventilation more easily. Because before that, the base ventilation rate wasn't determined, which meant every time you wanted to do it, you needed to figure out what you wanted it to be and then explain that to the code official to get a variance. Nobody likes variances. So now it's not. Now it's a normal thing you don't have to get a variance on. Normally, like I said, we're trying to be, controls-wise, we're trying to be 700 parts per million above the outdoor air level. So if you're like at 400 outside, that's putting you at like 1100 inside. You're kind of in that ideal range. City of Chicago, you're at a fixed 1000, also in that ideal range. If you go into buildings with a handheld meter and you're up in these numbers, the building's underventilated. You need to provide them more fresh air. If you're down here and you're seeing numbers like this, it's either in economizer mode, which is then it's fine. I don't care if it's overventilated during economizer mode because I'm getting free cooling. Or if it's not economizer mode, meaning it's a cold day outside where I need heating, or it's a summertime day, then I see these low numbers, I know that I'm actually overventilated. All right, I'm going to skip a couple of these to get us back on time and mainly answer some of those questions Tom was talking about. The reason these things became more popular, energy costs go up. Energy codes allow and or require this. Sensor costs have gone down over time and become significantly more reliable. So Tom's question, what's the service life of a typical CO2 sensor? Most of the manufacturers, they get what I call the CO2 engine or CO2 cartridge from one of like 2 manufacturers. You can find like 10 manufacturers of CO2 sensors, but most of them are getting their guts from one of 2 places, typically via Honeywell Analytics or via GE Sensing. Most of them are getting them from those places, and they design for a 15-year lifespan. And then depending on the model of product, they either give you a 10-year warranty or a 5-year warranty on the sensor. Just depends on their marketing strategy and all of that. So the service life question, Tom, is 15 years. But if you want to go more based on what the warranty is, you could probably say 10. But that's kind of your range. If you have a 10-year warranty and the sensor goes out of calibration on year 7, most of them are no longer calibratable. We used to have a button on a lot of them. You take the cover off. You could flow gas through there with a tube from a tank, and then press the 0 out button to kind of wipe it out. So we'd flow nitrogen through there, press the 0 button, 0 it out, basically recalibrate it to nothing, and then let it roll. The problem with that is there's a button on there, and people that aren't comfortable in the space for temperature or humidity reasons, they start effing around with stuff. Same thing with the paper clip or the guy on the ladder I was talking about. They end up pulling the sensor off the wall. They see a button, assume it's the main master reset button, press it, but there's no can of gas flowing, and they just jacked up the whole CO2 reading. So most of the manufacturers of commercial grade sensors have removed the calibration button on there. And if you get one that goes out of calibration in the warranty time, they just give you a new one if you happen to have that scenario. If you get industrial sensors, it is different. Those are calibratable, but those are going in a different type of building where the occupants tend to not push buttons as much, theoretically anyway. As far as calibration stuff, most of the manufacturers have an automatic calibration routine. This one is the one from GE Sensing. They call it automatic baseline calibration, ABC. Honeywell has a similar thing going on. And essentially the way this works is if a building is unoccupied for a certain amount of time, typically at least unoccupied 4 hours per week, which is most buildings, because most buildings are unoccupied at night anyway, right? There's enough leakage in and out of the building over a 4-hour time frame that most buildings become neutral with the outdoors. So the amount of CO2 inside and outside becomes the same as long as there's nobody inside breathing more CO2. 1 or 2 cleaning people, not a big deal. I'm talking about a fully occupied office here. So what ends up happening is that these sensors at night, when they go unoccupied, they keep calibrating themselves back to their original baseline. They know every night it gets back to that low-end baseline, whatever that is for outdoors, and they keep calibrating themselves back to that. So this was showing that over the course of, I don't know, 2 weeks, it looks like. This is the same kind of thing. What is this? This is 3 sensors over the span of a week, and they're a little bit further apart, and they eventually, over the course of the week, end up getting numbers that are plus or minus 20, 25 parts per million of each other, which is basically the same number in the terms of this horseshoe hand grenade type measurement. Here's 3 sensors over 2 weeks. Here's 3 sensors over 3 years. In this case, with a certain known CO2 concentration in a chamber, and watching them keep constantly calibrating themselves back to baseline with each other. So it has become significantly more reliable, which helps a lot. The first CO2 job that I did was in 1999, I think it was, or 1998, I don't remember. And at my boss at the time, a year later, said, "Hey, you got to go back out to such and such building," actually 2 different buildings we had at the time, "and calibrate those CO2 sensors." I'm like, "Why? Something happened to him?" He's like, "No, you just got to do it every year." I was like, "Good Lord, we got to do that every year? There's like 40 sensors. We got to do that every time?" He's like, "Yeah." I'm like, "Well, that's stupid. We should stop selling those. That's a lot of work." We weren't in the service business. We were in a distributor, so that wasn't really helping us any. But with the automatic calibration routines, we didn't have to do that anymore. So that automatic calibration, along with the costs going down on sensors and the energy codes being favorable to CO2, really started the growth pattern on there. So we're trying to get the actual occupancy ventilated, not ventilate extra if we don't have to, guarantee that we have the right ventilation to comply with code, and have the building automation data trends to prove it if we ever needed to prove it, comply with our codes, both energy and mechanical codes, and get people a pretty decent payback in that scenario. All right, anybody has any questions, type them in. If not, we're going to hit filtration, and then we're going to do our break. So for those of you that joined us a little bit later, we have 8 PDH questions. We've already done 2 of them, but if you joined us late and you answer the other 6 right, you should still have enough right to get your PDH credit. And we are halfway through or so. We're going to take a 10-15 minute break for coffee, bathroom, all that good stuff. So let's do filtration, and then we'll get to our breaking point. Although I probably shouldn't mention breaks. I guess you guys take a break whenever you want. It doesn't really affect me. I'll need to take a break halfway through. You guys can just put your phones on mute and keep on rolling with your day. All right, so filtration. So in order for us to filter stuff, or at least try to filter certain things out of the air, I have to know how big the things are, or at least approximately. If I don't know how big they are, I can't plan a filtration system to catch them because I don't know what they are. So this section in green right here is showing you very common things. Along the top here is microns, so micrometers, if you will. So small stuff on the left, big stuff on the right. So in this case, sand is the biggest thing on my chart that I'm trying to catch over here. But I also have hair on the chart. I have mold, bacteria, some small stuff. Viruses are much smaller, obviously harder to catch than sand. Gases, which are even smaller. Gases are really hard to catch with a filter because there is one gas that I want to go through the filter. It's called air. I have to have it going through, which means if I make it so restrictive it blocks my other gases, it's probably going to block most of my air, which is going to be a problem. So if you want to eliminate gases of a certain type, you're probably going to have to do it with something other than a filter. But let's see how big some of this stuff is so we can try to catch it and then determine what we have to do. If you prefer a visual, maybe this is better for you. This is 1 grain of sand, right? Approximately 90 micrometers. Here's some human hair, a little bit smaller. Here's PM10 and PM2.5. What does that mean? Particulate matter, 10 microns. Particulate matter, 2.5 microns. Those 2 are very commonly measured points. A lot of the handheld meters that you can get measure those 2 numbers. So that becomes pretty useful. But they could have just as easily picked 9 and 4 as the 2 measurement points. They didn't. They picked 10 and 2.5. So that's why they're on the chart here. And then over here at the end, there's this little tiny dot, and that's the approximate size of the SARS-CoV-2 virus at 0.12. So it's pretty small, way smaller than sand or hair, or even smaller than the 2.5 measurement that most of us look at. One last way to look at it, if you prefer, this is a PM10 over here, this black blob. Here is one of your red blood cells. There's PM2.5, smaller than your red blood cells. So this is a pretty small thing here. Bacteria, even smaller than that. And then this is not your SARS-CoV-2. That little dot is, that's a blown up version of him because it looks cool. So that's that little guy there. So it's pretty small stuff that we're looking to get here. Most of these viruses and things are not an exact size, just like hair could be a little bit thicker or thinner, and you could have a piece of sand that's a little bit bigger or smaller. It's approximate size. The same thing with these viruses. So some of them are a little smaller, some of them are a little bigger, so it's a range. In this case, this data came from somewhere different than that data did. That's why it's slightly different. But they're saying the average size here was 0.11 on their particular study. This was on a CDC website, at least at one point in time it was. So 0.11. What does that mean in the grand scheme of things? Well, other stuff like the flu virus and it sounds stupid, but the original SARS before we had the coronavirus causing SARS. Well, I guess SARS, the original SARS virus was a coronavirus also. But all these guys, you see they're in the same kind of general bucket of size. So if I can design a filtration system to catch one thing, it'll help me with others. So if you're no longer concerned about catching coronavirus, you don't really care. You're like, oh, we're almost done with that. We're out of that. We're in the clear. If you will, I don't care. I'm designing a system for that. Well, if you design a system for that, it's still going to help you with all the other germs that are going to be there. And whether coronavirus is here forever, possible, or whether it goes away, unlikely, you still have all kinds of other viruses and germs to catch. So if we're designing for these small things, 0.1 type size things, it's going to help me out. A HEPA filter is a common recommendation to deal with that. And you'll see 99.97 and 99.99% HEPA filters. What that means is it catches 99% of stuff that is 0.3 microns in size. It doesn't do as good with smaller stuff because obviously smaller stuff fits the gap. It still does really good though. 80% of stuff that's 0.11. So based on this particular study, 80% of the flu virus and coronavirus type size things will be able to be caught with a HEPA filter. Right? In general, compared to my other chart, coronaviruses and flu viruses are on the big side. They're big dogs. In fact, that coronavirus at 0.125 or whatever is kind of like even bigger than some of these the average span we had on this other chart. It's pretty easy to catch in the grand scheme of things. It's not as easy as sand and hair, obviously, but as far as viruses go, it's one of the easier viruses to catch. So some of the things we're talking about here will be fairly effective against SARS-CoV-2. So for filtration in general, there are 3 types of filtration systems: mechanical, electronic, and chemical. We're going to focus on mechanical systems. Electronic would be, I'll have this electronic commercial filter here. You've also seen electronic filters at houses. They were really popular in the 80s and 90s, not so much anymore, but they were. But they'll have electrical wiring going to any of these electronic filters. And what those guys do is as air is coming through there, they have a grid that charges the air. Let's just say, for example, it charges the particles positive. Then they have these plates over here after that grid that are charged negative. If I charge the particles positive, I got a negative plate. The things cling to the plate, and hence I've caught them. The nice thing about electronic air filters is they have very low pressure drop because a bunch of plates lined up. And air can get through there pretty easily. Not a lot of restriction. So I don't need a lot of fan energy to push air through an electronic filter. The bad thing about electronic filter is that once the plates get covered in stuff, they do a really good job of catching stuff. But once they're covered, now I got to clean them off so they can catch more new stuff. And the problem with electronic filters historically has been people don't clean them. Or they clean them the first few times, first couple months, and by year 2, they've stopped dealing with it. It's fine. Okay. They ignore it, right? And then it doesn't do anything anymore. And it's a bad filter. It doesn't keep your coil clean. It doesn't keep your air clean. Americans in general, not to pick on our whole country, but we don't like cleaning things. We like disposable stuff. Many of us use paper plates at our own home out of laziness because we don't want to wash the dishes. And we have a dishwasher. We still use a paper plate because we're lazy, right? We use disposable diapers for a reason. We don't want to do diaper cleaning and laundering, right? We're lazy. Same thing with filters. We want to throw a filter away every 2, 3, 4 months and put a new one in, and then that's it. We don't want to scrub down anything. So I'm not going to spend much time talking about electronic filters. We'll circle back to them in a little bit for some specialty ones. But in general, electrostatic filters are there and available. Chemical filters are a whole nother category of stuff that's more industrial related. You're not going to be doing that in an office building or school or anything like that. It's a specialty thing. So we're going to focus on mechanical filtration. If you have a mechanical filter, it means you are going to physically block the debris from getting through. There are 4 ways that we are going to do this: impingement, interception, diffusion, and straining. These are some examples of those. On each one of these, in this example, we're showing dust as our piece of debris. This is the airflow going through my system. And this blue item is 1 fiber. So if it's a fiberglass filter, it's 1 piece of glass. If it's one of those mesh plastic filters, right, that you can hose off, which no one wants to clean, by the way, it's just one of those little tiny fibers on there. So in this case, I'm a piece of dust. I come flying down the airstream. I slam directly into this fiber. Boom, hit the brick wall. That's it. I'm done. I slammed in the brick wall. My car's totaled. I'm just chilling out there right now. I'm impinged. Interception, I didn't smack the brick wall. I had more of a glancing blow, right? So as that piece of debris comes along the side of the fiber of the filter, it has a glancing blow, just like your car wheels on the road or your bike tires or whatever it is. There's friction between two things like that. And as the friction is there, it's slowing my piece of debris down until it comes to a halt. That's called interception. Straining, that's the easy one. That's the one we all think about. This is literally like a pot of water with pasta in it and then a strainer. You dump it through. The water is small enough to fit through the holes. The pasta doesn't fit through the holes, right? I strain it because it's too big to fit through. When you put the pasta through the holes, put the pasta in the strainer, some of the pasta blocks the holes. And then you got to kind of shift it around a little bit to get the pasta to move to get the rest of the water out. The big things fill the holes up on me. The same thing's going to happen here. I got two pieces of fiber. My dust can't fit through the hole. His butt's too fat. He clogs up the hole. But now that means the other things can't get through, like air. So just like the pasta in the strainer, when the pasta clogs the holes up, the water can't get out those particular holes. While here, if dust clogs the hole up, air can't get through. The good news is that the more dust and debris that I have on the filter, the more dust and debris that I'm going to catch. The dirtier your filter is, the more stuff it can catch. The filter actually gets better when it's dirty. However, if you can't move air through the filter, it is a worthless filter. So we have to change them, not because they're dirty and I don't want the dirt on there. I got to change them because I can't move enough air, or I can't move air in an electrically efficient manner. So you do have to change filters, obviously, and we're doing it based on their inability to move air. But in any case, that third method is called straining. The last method is called diffusion. This one's a little bit harder to explain. Two things have changed on this particular graph. One, I'm no longer using dust as my piece of debris. I'm using something significantly smaller than dust, in this case, a virus. And I no longer have the dust going in a straight line. I have the debris going kind of in this zigzag pattern. That's because when things get really, really, really small, like a virus, they no longer care about a couple things. One thing, they really don't care about gravity anymore. I'm sure you're aware of gravity, right? I'm sure you've all experienced it when you've tripped and fallen, right? That is the earth and your body and anything, for that matter, being attracted to each other. All the objects in the universe have this attraction to each other. They're pulling towards each other, right? It's a function of their proximity to each other and their mass. Well, the earth obviously has a lot of mass, and I don't have very much mass. So the earth is pulling me down to him. I'm technically also pulling the earth up. It's just I'm not doing anything. I'm too small. So the earth is pulling me down, right? All the objects are doing that. Well, if I'm a virus and I'm really, 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 really light, I'm almost zero weight, right? The Earth's gravity on me is pretty minimal effect, right? Other things can move me around much easier than the gravity can. Yes, technically, if everything in the room was 100% perfectly still and I was the only thing in the room and I was a virus, I would fall down to the floor. But there's other things going on here. So gravity doesn't matter that much for really light things. Airflow doesn't matter that much for things with minimal surface area. So for example, if you got a sailboat and the sail's up and the wind blows, the boat moves pretty good, right? If you put the sail down and it's just a mast there, the airflow blowing on the mast and maybe the back of the boat doesn't move it that much. Sail up, a lot of surface area, moves it a lot. Sail down, moves it minimally. The same thing's going to happen with a virus. It's so small that the air coming along it barely does anything to it. It doesn't have any surface area. It doesn't have a sail, if you will. Whereas other stuff in the air is bigger and it can get blown around more easily. So the main mechanism for our motion in the space is going to actually be Brownian motion. That's what we're trying to, oh, I lost my thing. There we go. That's what we're trying to illustrate with this red zigzag line. You guys can all see my little pointer thing when I keep doing this, right? The little red thing. Hopefully you can, because I've been doing it all morning. It's showing that zigzag line. What that is it's things bouncing off each other. Little tiny particles, boom, slam, bounce. They both go in different directions. Then they bounce into somebody else. And they bounce into somebody else. That Brownian motion is the main driver of small particle movement. Thanks, Matt, for letting me know the cursor works. That's the main driver of the particle movement, more so than airflow or gravity. If gravity was the main thing, great. All the viruses would fall on the floor. We'd vacuum them up every night or wipe them off the counter. We'd be good, right? But that's not the case. And if airflow was the main thing, fantastic. Just suck all the air back into the air handler, put it through some really awesome HEPA filters. We'd have it all. Great, fantastic. But that's not the case. So catching viruses with a filter is very difficult. Yes, I can catch, 80% of them in a HEPA filter if I can get them to the HEPA filter. That's the challenge. So anyway, when I do catch them, they bounce around on here. The diffusion part, when they're like really close to each other, the molecular collision of those things, they adhere to each other. They're getting bounced around off all these other things, and they finally hit this fiber, but there's no bouncing on the fiber. They come in contact with each other, and that I don't want to call it gravity. It's not gravity. Whatever that attraction is between two bodies, I forget what it's called. They hold each other together when it finally does get there. If it ever gets there, it may or may not ever get there. When you're picking a filter, the efficiency, which we'll talk about, of the filter is important. The pressure drop is also important. I can get a really, really awesome filter, but if I can't push air through it, it doesn't matter, right? And how much CFM I need to shove through this guy. There are two filter efficiency tests. One of them is very badly obsolete. It is now 30 years obsolete. So if your master spec refers to ASHRAE 52.1, or it refers to dust spot efficiency, or it has any type of percent in your air handler schedule in the filter notes, it is badly obsolete by 30 years. Stop using it. There's no such thing as a 30% filter anymore. Those we're way past that. Stop doing it. The current standard is ASHRAE 52.2. That's the Merv rating system. So instead of saying I want a certain percent filter, you'll say I want a certain Merv rated filter. And that came out in 1999, and I think we're still in the 2012 version of that. Not that your consumer would care about this, but the way it basically works is here's the filter you want to have tested. This is not a test you do in the field. This is a test that the filter manufacturer has done in a lab. They run air through a really, really, really good HEPA filter to kind of get it all pretty clean to start off with, right? By the way, this ASHRAE 52.2 test for Merv rating is not for HEPA filters. HEPA filters do not get Merv rated. This test is for things that are less than HEPA. All right, so they run air through a HEPA filter. So I start out with pretty clean, neutral air. Then they have a particle generator spew a bunch of aerosol into the air of different size components. Maybe they test some 0.3 stuff, they test some 1.0 stuff, etc. They have a particle counter to count to see if they put in as many particles as they thought they put in. They run it through your filter, and they have another particle counter to see how many are left. So however many percent you can catch of a certain size thing will determine your Merv rating. This is the Merv rating scale. It goes from 1 to 16. Yes, I know that my chart has 17 through 20 on here, and it says HEPA. HEPA is not officially part of the Merv rating. It's in the commentary section of the standard saying basically, hey, if you did rate HEPA to hit this, it would be in the 17 to 20 range. But this test is not for HEPA, so don't think about it too much, basically. But it stops at 16 officially. And the size particles you can catch get you your Merv rating. So if I want to catch some, let's just say this, your normal air handler rooftop default filter is going to be like a Merv 6 or a Merv 8 in there. It's not that good. It doesn't catch that much stuff. The main purpose of a regular filter is to keep debris off of the evaporator coil so my evaporator coil can still do a decent job of heat transfer. Because if the coil gets dirty, then obviously I got to cool down the refrigerant, to cool down the coil, to cool down the fins, to cool down the debris, and then cool down the air. I got another layer in there. So it's mainly to keep my coil clean so I don't lose cooling capacity and cooling efficiency. It has nothing to do with your health and well-being. If you want health and well-being, you need to get down over here. So if you want to catch germs, like say you want to catch something that's the size of a virus like influenza or SARS-CoV-2, we said that was like 0.10, 0.11, 0.12 type range. That's down over here, right, in the 13 through 16 range. So I need to be down in over here. If you look at any of the recommendations from ASHRAE that came out after COVID, one of the recommendations was to get your system. It was like weirdly worded too. It was like get your system up to Merv 14 level, right? Because that was going to catch an appreciable percentage of the SARS-CoV-2 virus, assuming you get the virus to the filter, which is another debate. And then it said if you can't do that for size and or pressure reasons, then at least get a Merv 13. It was kind of weird that they gave you like two options of a recommendation. They're basically saying Merv 14 is what you kind of need, but if you can't do that, Merv 13 is decent. It helps. Anything below Merv 13 is pretty much doing almost nothing for virus control. Right? So you're getting a Merv 10, 11, 12, it doesn't do much. Right? If you look back on our chart over here, right, the stuff we were catching, right, that 0.1 was where we were at with that virus type stuff, right? So that's down over here. in this range. All right, we're ready for our next quiz question. I can figure out how to do it. All right, quiz question number 2 of 8. What is the current ASHRAE filtration standard? Is it 52.1 dust spot, 52.2 MERV, 62.1 indoor air quality? And let me see. We don't have any other questions typed in. Feel free to send questions, and man, I'm going to get bored with you guys if you don't make me answer something. Even if I answer it wrong, at least I'll be able to answer it. I'm kidding. I'll try not to do it wrong. All right, we got 80% of people that have answered. I'll give another 15 seconds, and maybe we get everybody to answer. For those of you that are barely paying attention, but you need your PDH credits, this will be the time to slightly pay attention and answer the question. Because if you don't answer the questions, you won't be able to get a certificate. I know many of you are multitasking, reading emails and stuff. That's fine. I'm not offended, but got to kind of halfway pay attention. All right, I'm closing this poll in 4 seconds. 3, 2, 1, closing it. Great job. I apparently did not make that one as hard as the last question because 83% of you got it correct. ASHRAE standard 52.2 with the MERV standard is our filtration standard for ASHRAE. 52.1 was the old dust spot. Thankfully, none of you answered that. That's fantastic. And some of you said 62.1, which is our indoor air quality standard, which is nice and it's important, but it does not have anything to do with my filtration rating system. All right, we are at 10:32. Let's take an 8-minute break, and we'll get back on track. So 10:40, let's come back and we'll resume where we took off. That allows people to get coffee, bathroom, etc. By people, I mean me, and we'll resume from there. And we'll finish up our filter discussion. Let's see if I can somehow put that on the screen. Let's see. There. All right. See you at 10:40. All right. We might be back in good shape here. All right, we did have a question come in. We'll try to address. What Merv rating would you recommend if your house has a 1-inch or 4-inch filter size and your wife and kids have allergies? All right, so the 1 versus 4-inch, we're going to address that actually right now and give you some options on that specifically. But as far as the Merv rating, and just so to be clear, as we talk about this, the Merv rating can be independent of the depth of the filter. All right, sometimes they're related, but it doesn't have to be. There's ways to get skinny filters with high Merv rating, but so there's pros and cons. As far as catching stuff, like if we go back over here to pollen, which is what, when you say allergies, I'm assuming you're meaning seasonal allergies related to pollen. Pollen is fairly big, right? We're in the, let's call it 9 microns and bigger. So it doesn't take much to catch pollen. If we look back at this chart over here, Merv 8 would probably get most of that taken care of. If you want to do a little bit of better job, you go to like a Merv 10, which is not that much more expensive than a Merv 8. I don't know anybody who makes a Merv 12, but there's Mervs 10s and 11s out there. I know Honeywell has a Merv 11. That would probably be a pretty good spot. You can certainly go better than that, and there's reasons to go better. But you probably only need like a Merv, 8 to catch most of the pollen-related stuff. On this chart up here, pollen's even in the really wimpy Merv category. I lost my laser pointer at some point. Oh, when I closed my screen. Pollen's up here in this category because it's almost 10, right? It's like most of it is above 10, so some of it's a little bit smaller. So pretty much any filter will catch pollen essentially. Any fitted filter that is fitted in your cabinet correctly. So if you're talking about allergies related to something else, then we could talk about that. But pollen is pretty easy to catch in terms of HVAC systems. All right, one of the other selection criteria, your filter, and specifically when you should change your filter. You should be changing filters based on pressure drop, especially if you have expensive filters. The more expensive your filter gets, the less often you want to change it, right? So the filter I use is pretty expensive. I want to say it's like $80. But I can usually get away with changing it almost on an annual basis. I change mine based on pressure drop at home because I'm a dork and I do things like that. At a house, you don't normally do that, but I do. But I've had it over the course of 5 years. I've had it last 11 months, 9 months, 15 months, 13 months, I think are the months that I changed it at based on pressure drop. So I got some pretty good usage out of that. Before that, I had much simpler, cheaper filters, but they didn't load as well as the expensive one, and I would have to change them more frequently. But in a commercial building, if you're going to be putting in high-end filters, right, you're going to be putting in something, let's say, better than a Merv 12, something that's going to cost some money, multiplied by all the filters in the grid and the air handler, multiplied by all the air handlers you have, multiplied by all the labor it takes to change them out. You don't want to just do it randomly like every month or every 2 months. You'd like to change it based on pressure drop, and you can certainly do that. The easiest way to do that is with a manometer to measure the pressure drop across it. If it's a large facility, the maintenance guys could probably measure them, get an idea of what they are, and then be like, okay, for air handler number 3, we pretty much need to do it every 4 months. But for air handler number 7, I can pretty much do it every 12 months, right? Just depends. Or instead of these, fixed metering devices, you could put on something that ties to your building automation system and have it report back to your building automation system and tell you when to change your filter. If you have a BAS, it's extremely cheap and easy to add that on there, like tens of dollars. It's not that big of a deal. So might as well have the system tell you when it's time to change the filter. More criteria that's going to be involved. If I want to catch more stuff, I want the air to go through slowly. The faster the air goes through the filter, the easier it is for the air to get through, right? Air moving down the duct system has both velocity pressure, directional pressure, and static pressure, pushing out all the different directions, right? The higher that velocity pressure, the more likely it can shove through my filter media. If I want lower velocity pressure, one way to get lower velocity pressure is to have lower velocity. That'll give me less pressure. Think of it like blowing a spitball through a straw. You could like really weak and you're probably not getting the paper out the straw. It's just gonna sit there. You got to blow it really hard to get that thing to come shooting out. You need a lot of velocity pressure to shove something through a space that it really shouldn't probably fit through, like paper through a straw. Same thing with these filters. So I need a higher velocity. One way to get a higher velocity is to get a bigger duct dimension. Let's see if I can, my mouse is killing me. There we go. Let's see if we can draw. I should have a drawing on here, but I don't. But let's just say that I have my duct coming through. I go to a wider section of duct, then back to a lower section of duct. Let's say that this is 1,000 CFM moving through this duct, right? Should have made this a quiz question. Well, then I'm also going to have 1,000 here and 1,000 there. The same amount of air going, assuming my ductwork doesn't leak, whenever air goes in to the fat part of the duct, comes out the skinny part of the duct. I didn't lose any air. My velocity could be a different story. This could be 1,200 feet per minute over here, right? And assuming the duct dimension on the outlet is the same or similar, let's just say it'll be approximately 1,200. It could be slightly less. But then in the middle part, maybe it's only 800, right? Because the velocity is the CFM, which is cubic feet per minute. Look a little algebra here today. Cubic feet per minute divided by the area, feet squared per minute, right? Cubic feet per minute divided, this is per minute. My handwriting's so bad, even in real life, right? That's going to be my velocity, my feet per minute. That's all that's left, feet per minute. So if I want to have the air slow down, I need to make the dimension bigger. If I go in your building and I say, hey, the ductwork coming in, let's just like double the height of that ductwork and put some more filter in that way and get more filter surface area. And you'll be like, dude, there's nowhere to double it. We don't have that kind of space. So what you get in a lot of cases is this V-bank scenario where I have all that surface area. And if you think of it like if you stretch out those filters like an accordion, you stretch them out, it's a pretty tall duct. I just happen to put them in a V shape to get them all to fit. So as the air goes through the V-bank, it temporarily slows down for that moment in time, if you will, just for that instant. And then as it leaves the V-bank, it's back up to the regular velocity. So that's one way I can do it. I could also put pleats in a filter. Let's see if I have a picture of a pleated filter. I'll skip ahead. I won't skip ahead. We're on a pleated filter. Bang. Literally the most common filter. I don't have a picture of it. I'm so bad. I do, but they're really small in there. Damn it. Well, anyway, these pleated filters, basically inside the filter, if this was my filter, not my filter rack, inside the filter, all the pieces of fiberglass would be in a zigzag pattern like that. And then you could, of course, put pleated filters inside a V-bank to kind of double the effect there. So I want to get that air to slow down as much as possible before it goes through the filter. It'll be easier to catch stuff. Plus, I'll have more surface area to collect the stuff on, which means I don't have to use my filter as often either. So these are the main types of mechanical filters that we have. Some of them require some discussion, some not so much. We'll hit them real quick. So I can have cheap low-end panel filters. They don't catch much. They're like Merv 5, Merv 6, if that. It's pretty worthless. A lot of times they don't even have a Merv rating because the manufacturer of them doesn't care, because saying that they have a Merv 5 or 6 filter is not exciting to anyone. So they don't need to even pay for a test. They're like, whatever, don't care, right? They're low-end filters. Do not use these as your air handling filter. They don't catch hardly anything, only big stuff. Big stuff means dust and pollen, nothing else smaller than that. The places that we do use them, where it makes sense, right? A pre-filter would be a great example. What's a pre-filter? You have a really nice, expensive filter. You don't want that thing to be clogged up with a bunch of big debris, which makes you change it more frequently. You put a pre-filter upstream of that to catch the big stuff, and you throw it away every month because it's cheap and you don't care. And then the good filter that catches all the tiny stuff can be loaded with only tiny stuff, and hence it lasts longer because they didn't waste it on the big one. It's a sacrificial lamb. That's the time to use a pre-filter or use a panel filter as a pre-filter. The other time we use it sometimes is during construction, when we tell the other trades not to run our air handler when we're not there, not to run our rooftop, not to run our furnace, whatever, and they do it anyway. I don't want my good filter in there. That's going to cost me a lot of money. I'll put a cheap panel filter in there to catch drywall dust because I know they're going to run it even though I tell them not to. Panel link filters, not common at all. You'll see them in certain units, especially multifamily in the, what do you call them? The gas pack type units. You'll see like, it won't be as big as this. It'll be like just 2 of them and it kind of goes up and like that. The nice thing about them is that there's no leakage really between them if you have more than one panel. but they don't really have any type of rigid framing, so you get a bunch of leakage over here anyway. So it's not really common. It's kind of junky. Roll filters, which you're hardly ever going to see anymore. I don't think I've only seen one of these. They were briefly popular and then immediately gone. They got popular briefly is because the idea was you can like wait years before changing them because they automatically change. Every so often, this little motor turns, which scrolls more of the material through, right? It automatically changes. It's self-changing, if you will. It's like when you were a kid and you go to the public place and they had that towel dryer thing. You pulled the towel down, you dried your hands on the cloth towel. The next dude pulled it down and dried his hands on the next clean section. It's like that basically, but with filters. And then every so often you would have to change them out. If you find one, it's probably broken or abandoned because it doesn't work anymore, or they can't find any cartridges for it, replacement rolls. Bag filters are fairly common. These guys require some depth though. I mean, you're talking about at least a foot of depth, if not more, on here. The nice thing about them is air is going down each one of these slots, and you have a whole bag of surface area, and then the whole back side of that bag of surface area. So you get a lot of surface area in a relatively short distance here. You do have to design around them. You're not going to be able to stick a bag filter in like a packaged rooftop. It's going to be an air handler, and you're going to plan for it when you have the air handler built. But you can do a pretty decent job of getting a lot of surface area on those guys. As you step up in a notch, you might go to a cartridge filter. This is going to be your higher Merv ratings. They're going to be more expensive because they're in frames. The reason they're in frames, you'll see in a minute, is so I can easily seal them when I put one next to the other. Whereas something like these, I can't seal it. All the air leaks around this thing so badly, it's horrible. And even there, to a degree, it's difficult to seal. You can actually do a decent job with bag filters. But these cartridges are pretty rigid, so it makes it really easy to seal. HEPA filters are pretty much always going to be rigid, either metal framing or sometimes really dense cardboard framing. But they're always going to be rigid because every HEPA filter has to be sealed to the next HEPA or to the rack. There's no point in having a really good restrictive filter and then as much air that wants to can go through this gap. The more restrictive your filter is, the more likely air tries to shove through the gap. So the better your filter is, the more likely you need to seal it. Seal it meaning like caulk it or gasket it in between. Speaking of gasketing, on the doors, if you have got a V-bank like this, when you shut the door, there needs to be gasketing material either here or on here to hold it snug against there. There's no reason to have any, half-inch or quarter-inch gap around a filter because most of the air just goes around the gap. The better the filter, the more important this becomes. So they're showing you your HEPA installation and sealing it into the frame. These are bag filters, but if you have a gap in between there, air is going to go through the gap. It's so much easier. So putting things firmly in the frame and then caulking them up in between stuff to seal it nice and tight is going to be key if you want to have big banks of cartridge or HEPA type filtration. All right, last few things on filtration, and then we'll move on to purification. We have been doing portable stuff. Obviously, this is a shameless plug for the Carrier portable unit. This was starting to become interesting like right when COVID was about to come out, and then obviously because of COVID, it got accelerated. And this particular unit was specifically developed for improved air cleanliness in like ICU rooms at hospitals. And there's different configurations for that. We use it in a lot of other applications now, other than hospitals, but that was kind of the original intent. So when it first came out, it wasn't called Carrier OptiClean. It was called the negative air machine for like 2 months, and then they started marketing it differently because COVID, made that possible. But the idea with these guys is that you're going to pull a negative in a room. So in this case, it's a hospital. It could have been a clean room or something like that. Probably not, but it's a hospital. They want the negative in the room. Actually, it wouldn't be a clean room. Clean room would be the opposite. You wanted that positive. Hospital, I'm going to keep negative because the biggest concern for me is the sick person laying in this bed. I don't want their germs getting into the hallway. I don't want their germs getting into the next room. So I keep their room negative, which means I keep the hallway positive. And then I have some way to exhaust air out of this guy. This picture probably does it better. Let me skip these two and do this. This kind of shows it a little bit better. So these are different configurations here. Here is a portable room HEPA filter directly exhausting outside. You're exhausting air before it leaves the building. That is one way to do it, to keep this room negative relative to the hallway and the other rooms. It's kind of stupid because like you're filtering the outdoor air or air that's going to the outdoors. So like at that point, just exhaust it, dude. Like, what are you doing? So people have been using this without the HEPA filter in there and just exhausting with no HEPA, right? You could also have the HEPA filter, and that only works with no filter if you're going to the outdoors. If you're going to have it exhaust and dump into the return, like we're showing there, you definitely need the HEPA. Or you can have the HEPA and exhaust it into a corridor and have the corridor take it back to the return somehow or to an exhaust system. Or you can use it in a recirc mode where it both sucks air out and puts the same air back into the room, so it's not a negative air machine in that application. It's just a recirculating extra filter on top of your regular HVAC. That, believe it or not, has become the most common usage for that because we're doing that in many more places other than hospital ICU rooms. Schools have been one of the big applications because obviously schools have a lot of kids in a room, obviously, and a lot of them are older buildings and they don't have very good ventilation to begin with. They got a bunch of, cabinet unit heaters in the room. And ventilation means open the window. But people don't like opening windows when it's freezing cold out, so they tend to close them, and hence no ventilation for the kiddos. So having a machine like this in there that's cleaning air the best it can helps out. We still have the problem that viruses are tiny, and they don't like to get stuck in the airflow path. So we'll get some of them this way, but there's still going to be some in the room that never get into the airstream. But this helps out quite a bit. If I can get a certain percentage of them, it's better than doing nothing. Usually we try to combine this. Let's say we're doing that classroom where they don't have good ventilation. We try to combine this room by room HEPA solution in combination with one of the air purification technologies to kind of double dip our efforts on that. Obviously, ducting in outside air and properly filtering and heating and cooling it would be the best thing. But if you're trying to get a school up and running in the COVID world right now, sometimes that's not in the budget or in the time frame. So all this tiny stuff we're trying to catch, we looked at this in a different view before, but the big concern is all this stuff over here. A lot of what we're doing with filters doesn't do much for things that are below the 0.1 micron size, because that stuff doesn't really care about airflow, as we discussed. So that stuff never gets back into the airflow stream and doesn't get filtered. So what does that include? Viruses, right? Stuff like that, small particles. Yeah, if it's dust and pollen and skin and dander and lint and all that stuff, we can get that over here. That's pretty easy. Plant spores, all that kind of stuff. But over here is the hard stuff. I'm going to need help with that. So we talk about viruses specifically. There's been millions of solutions. I probably should take some of these slides out. I'd hit some of them. I probably should hide more because at this point, I kind of feel we're almost done with the mitigation stuff. I don't know, maybe not. But this is 2 years old now. And this is funny because like a lot of studies agree with this. And if you're like me and you argue with the people, at your school district and other school districts in the area, and they were super concerned about this 6-foot rule before they let our kids go back to school last year. And I would just be like, the 6-foot thing is like, it's made up. Like, it's not even a thing. Like, there's no study that says 6 feet is a safe distance in any way. Nothing. It doesn't exist. It's not real, right? And germs go significantly farther than that. There's some studies that show they can go as far as 90 feet out of your face when you're sneezing. This one was an MIT study, and 26 feet when you sneeze and cough, right? 26 feet and 16 feet. It's pretty far distance, right? So the 6-foot thing was kind of just somebody saying, hey, that's a pretty good average of what's reasonable, right? Schools, as you know, 11 months ago, switched their rule from 6 feet to 3 feet nationally. Only schools, nowhere else. The 6-foot rule stayed everywhere else. Why did they switch it at schools? They realized they literally could not fit all of the kids in a school and keep them 6 feet apart from each other at all times. There's too many kids for the amount of space. Couldn't do it. So they changed the rule to accommodate what they had. Well, if the rule can be changed that easily, obviously the rule is not based on anything concrete. Long story short, germs will be floating around your room. They're not going to care about the gravity. They're not going to care much about the airflow. They're going to float around via Brownian motion. They're going to last in the air for 8, 10, 12, 15 minutes, floating around, doing whatever the hell they want. So I can't rely on distance being my saving grace. I can't rely on HEPA filters being my saving grace. I got to do something else to try to get either kill or neutralize these guys or capture them better in some way. That's what we're going to focus on. So one of those technologies is a solution that we have from a company called Secure Air. Some of you guys that have been doing work with us for years have probably heard of this. We started using them, I want to say in 2013, specifically for hospital and clean room applications. Prior to that, we used a company called Stryon Air. A lot of the guys that work at Secure Air used to work at Stryon Air. And when they moved over to Secure Air, we kind of moved with them. So we've been doing similar, different, but similar technologies. Similar meaning they have 2 different patents for similar things for lots of time with hospitals and stuff now. And that technology has now made its way into simpler systems like schools and office buildings as well. But the basic premise of this technology, I'm going to skip a couple slides because it's repetitive of our filter discussion. There's lots of small things in the air. Filters don't do a great job of catching the small things. How many small things? Most of the things are small. These are the kind of things that I can catch with a filter easily. These are the kind of things I can't. There's a lot of them, tons of them. And some of them are the things that I'm a little bit nervous about, like a virus or something like that. So what is the small stuff specifically? Start plotting some of these on here just so you can kind of see them. For some reason, my slides are going slow. All right, there we go. They're all up. So this line right here is kind of like representing what the things above that are a little bit easier to catch with a filter, right? The things below that are harder to catch with a filter. Pretty much all the virus stuff, cold virus, influenza, H1N1, all that kind of stuff. It's harder to catch because it's small. So what does this technology from Secure Air do? The thing they have is called active particle control. Write that down. You'll link me later. Active particle control. What does it specifically do? Why does my mouse thing not want to play nice? All right. So first thing is we're going to condition the particles as they're coming through the air. What does condition them mean? Essentially, it means we're going to charge them. Just like those electrostatic filters, we were charging particles one way, let's say negative, and then we had plates positive where they would collect. We're going to charge particles. But this time, we're not going to charge them and then have a plate to collect them. We're going to charge some of them one thing, say positive, and charge some of them a different thing, negative, and then they'll collide into each other. So I'm not charging plates to collect them. I'm charging things, and they're colliding and sticking together. A bunch of positive negatives clumped together, and guess what? Now I no longer have small things. Now I have, well, I still have small things, but they're bigger. They're slightly bigger, right? So instead of them being 0.1 microns, they're now 0.2, 0.3, 0.4 micron clumps of things, which means they're more likely to get caught in my filter because I've made them bigger. So I can do this to collect really small things on my filter, and I can use it to make the Merv rating of my filter better than it is. If I built a filter that by itself without electricity was going to be like a Merv 12 filter, and then I apply this active particle control concept to it, my Merv 12 starts behaving like a Merv 15. Even though density-wise, material-wise, it would have only been a Merv 12, but now I've got these things that are bigger, so it's kind of like the equivalent of having a Merv 15. You can't just do that and then have the filter and say, I made my Merv 12 a Merv 15. It has to be rated together. When you do the ASHRAE 52.2 Merv rating system, the whole thing, the whole assembly is rated. So Secure Air does that. It's all in one box, if you will, and the whole thing gets rated as the filter. So the media density has the pressure drop feel of a Merv 12, but the rating ends up being a Merv 15, which is kind of cool. The other nice thing that happens is that if stuff is charged, but it's still small enough to get through the filter, which is right after the charging rack, it goes out into the space. Now I have a bunch of stuff in the space that has a charge to it. Stuff in the space with a charge to it adheres to other things in the space and makes those things bigger. So it can jump onto whatever's in the space that I can have multiple things in there, and if they have a charge, a virus or whatever, they can clump onto each other, and these things get bigger. Now, once they're bigger, they can either fall to the floor because they're heavier and gravity matters, and they get vacuumed up, or they have enough surface area, they might get caught in the airflow path a little more easily and make their way to my filter. So not only is this helping me with stuff that capturing stuff at the filter, it's actually active, hence the name active particle control, because it's in the space actively collecting things and bringing them back to me. From a visual standpoint, this is just showing you a commercial grid. By the way, there's a residential version of this now. The residential one came out, I want to say like 2 months before COVID started in the US. So they were already working on it, and then they probably saw the writing on the wall and kind of sped up the release date. So if you need one for like your house, it's a thing, you can do it. But most of what we do is commercial, hospitals and clean rooms and stuff like that. So the active particle control is really multiple components. It's that collider, that particle control collider thing we were talking about, along with the physical filter media bundled together into one assembly, if you will. So these guys get a Merv 15 rating. That's how they're tested and rated. The pressure drop is reasonably low, 0.28 inches at 500 feet per minute is actually pretty good. Some of these are much higher than that for that kind of level of filtration. We're doing a pretty good job of catching the biological stuff, which means bacteria and viruses. A pretty good, here it says inactivation rate, and they also say kill rate on there. And since then, they've scolded me about saying kill, so I should change my slide, but I'm not going to because I like saying that. And then whatever doesn't get collected in there goes out into space with a charge, and thereby collects other stuff too. This filter rack is 9 inches deep, so you're not putting this in a packaged rooftop. This is an air handler type of thing. Typically, they'll be in banks, just like other large filter racks. These are 2 foot by 2 foot banks because this is a large air handler, but it could be any type of configuration. You could have, 4 foot tall by 6 foot wide air handler, just these ones, for example, right? And you can get whatever sizes you need. They're kind of built to order. They do make one that goes downstream into the supply duct. It's not super common to do this. Mainly because we usually just design the air handler for it, but also because this velocity requirement in your existing ductwork, you're going to have relatively small ductwork. So you're going to have 800,000, 1,215 feet per minute in the duct. Yes, you may be 500 feet per minute at the evaporator coil because you have to be or you get water blow off. But the ductwork, you're going to have a higher velocity. So retrofitting this in the duct is not common at all. Typically, it's in the air handler, and we design the air handler around this component. The other nice thing about these guys is the way those filters load up. They can load from I don't know how to explain it, but if airflow is going that way, they kind of load from the back forward, and they use the whole density of the material as opposed to just the face of the material. So it takes longer for them to fully load with minimal pressure penalty. So you tend to get a long time out of them. This is showing 15, 16 months, and then I'm going to probably want to change it. Versus my regular filtration system, I may have been changing it every 3, 4, 5, 6 months, depending on your application, obviously. But I tend to get 2.5 to 3 times the filter life on the cycle out of that thing. So yeah, you're paying a lot more for the filter because it's a special filter, but you're not changing it as often, so there's a kind of a trade-off there. By the way, originally when we were doing some of these, we were doing it for energy-saving projects, right? A hospital that needed good filtration, they wanted that Merv 1415 filtration. They could do this because it's only a 0.28 inch pressure drop. They could do it at a relatively low fan energy, which was a cost savings mechanism. That was literally what contractors and engineers were explaining to the hospital guys. They were selling it to them based on energy saving projects. And since then, we're obviously doing it for other reasons now because it does a good job of catching germs. But it was really an energy saving project is how this kind of started for us 10 years ago. But like I said, you're only going to do this on air handlers where I have the ability to have space to fit one of these things. If you got, say, a packaged rooftop unit, this isn't going to work. You're not going to have anywhere to put that. You're not going to have anywhere to put 9 to 12 inch depth widget. So one of the things that we have been doing on packaged rooftop units is 1 and 2 inch air cleaners from this company called Respicare. We've been using Respicare anyway residentially for, I want to say 8 years. But now I've been doing stuff on rooftops with them with 1 and 2 inch cleaners. And the reason they're 1 and 2 inches is because that's the size of the racks you already have on a rooftop, so they fit there. They have 24-volt power that comes to them. 24 volts is low voltage, so I typically don't have to put it in conduit for most codes. And I have 24 volts readily available in most rooftop units. By most, I mean all. So it makes it pretty easy to set this up. What this is pretty low-end, cheap filtration media. This thing closes and latches down. But then there's a charging grid inside there. This is a Merv 13 filter. That's about the most they can get out of a 2 inch or 1 inch assembly. But still, Merv 13 is pretty good and catches a decent amount of small stuff, as we saw earlier. And it's relatively low pressure drop, 0.15 to 0.2 inch pressure drop, which is pretty good. The power consumption is low, 2 watts on a 24-volt connection. That's basically 0, not really any energy penalty. And then you can get multiple configurations of sizes, and you can also use multiple sizes to slide them in together. But it's kind of nice. And then this grid charges stuff, which makes things bigger, and they're more easily caught on the filter. Same kind of concept, just like a little mini version of it. So keep that in mind for those kinds of applications. All right, quiz question number 3. Everyone's welcome to answer once again, but the people that need PDHs have to answer. All right, which technology does Secure use to bring the small particles back? Active particle control, bipolar ionization, photocatalytic oxidation, or HEPA filtration? And then if you guys have any questions you want to ask me, please type them in the chat box, and I'll do my best job of answering them as best I can. It's like 67% of you voted. I'm going to give you 10 seconds because we need to keep moving because we have, 6 hours of material to cram into 3 hours. It's my fault. All right, I'm closing it in 5, 4, 3, 2, 1. All right, correct answer was the very first one, active particle control. That's why I said write it down. Pay attention, write it down. I was trying to give you the answer. I was trying to be cheap. All right, here we go. Moving back on. All right, UV lights, our next topic of discussion. This is not new, so we should be able to go through it quickly, but there is some things you definitely have to understand. UV light occurs naturally, comes from the sun and other sources. Obviously, the sun is putting out pretty much like every band of light possible comes from the sun. We are going to fixate our life today on two of those. UVC band and UVV are the two that we're going to focus on, specifically 254 nanometers and 185 nanometers. So all that stuff comes naturally from the sun, comes into the space, all that good stuff. We're going to recreate that artificially. If you didn't know, light from the sun will kill germs. Some of you guys have been in my other IAQ classes, probably heard me say this, but like on my honeymoon with my wife, which is now, 19 years ago, we did like a little catamaran cruising out to some island for the day with a couple other people. And the dude that, drives the boat, pulls it up on the beach. He takes a bowl of fish, sets it on a stump on the beach, squirts some lime juice in it, and starts walking away. I'm like, hey, dude, what are you doing, man? You can't just leave a bunch of raw fish on the beach. He's like, yeah, we're having that for lunch. I'm like, dude, that's disgusting. He's like, well, that's what we're having. It's like, what? He's like, yeah, the sun, it kind of cooks the fish. It like cleans it. I was like, okay. Didn't really believe him at the time, but I was hungry, so we ate it for lunch anyway. But later on, researched it, and the UV light kills the germs on the surface of the fish, or anything else for that matter. Right? UV light will kill single-cell organisms. When you walk outside, your skin is exposed to the sun. The sun shines on it a long time. Your skin cells get killed off. You see them peeling off. They fall off and die. It will kill single-cell organisms. Well, the kicker is, if you're a single-cell organism, you only got one cell. You get killed, you're dead. My skin, yeah, each one of those is an individual cell, but below them, there's a whole bunch of other layers of skin. I have unlimited layers of skin, so I'm good. Granted, over time, it can cause skin cancer, so, use your sunscreen. But in general, it's going to kill stuff. UV light will break down the DNA of pretty much any small organism, right? Any cell for that matter. 254 nanometers seems to be the magical wavelength that we focus on. And then here's the money for the day. Here's the main thing down here. I call it the kill dose. It's properly called the CT value. It's actually a measurable, calculatable thing. It has units of measure, microwatt seconds per square centimeter. Don't try to say it really fast. Microwatt seconds per square centimeter. It is a function of the intensity of the UV energy source, i.e. the sun, light bulb, etc., and exposure time. The longer you stand outside in the sun, the more likely it kills your skin cells. The longer the fish sits on the beach, the more the sun is going to be killing germs on it. I need a lot of time or a really large energy source or a combination of those two. So if I put a UV light in your duct system, let's just say that 1 inch away, I'm at full power. If I get 2 inches away, I've lost 75% of its inactivation killing power. If I get 8 inches away, I've lost 98% of the power. Things that go close to the bulb are more likely to get killed. Things further away, less likely, unless they're there for a long resonance time. I saw this chart on a Honeywell presentation 2 years ago, and then I went and found the source of their chart to make it a little more meaningful for our discussion today. This was using one of their products with a 600 watt centimeter squared light bulb sitting at 1 foot away. I went and found a different bulb that's even more powerful. I believe it was a Phillips bulb, and I based our calculations off of that. It was the most powerful I could find at the time. But anyway, this chart, and I can send a link to anybody who wants the chart. It comes from the American Ultraviolet Association or some weird name like that. But there's a 90, a 99%, and sometimes a 99.9% COM, which is not shown on here, of the dosage rate, the kill rate, microwatt seconds per centimeter squared, you need to kill certain things. Here's a bunch of bacteria. Here's some mold. Here's some viruses down over here, right? So 90% means it'll kill 90% of them. 10% of the bacteria will survive. 99% means 1% of the bacteria survives, and so on, right?
So if I take an example, I forget which one I took, Bacillus subtilis, whatever that means, I need 5,800 microwatts seconds per centimeter squared to inactivate 90% of that, right? So if I get a light bulb that's 800, that's my intensity of the light bulb. I divide that into, oh, actually I did 1100, right? I did the big one. I did the 99%, so 99% kill right here. So I did that. Did my math wrong? I wrote it wrong, right? Wait a minute. No. I did the spore. That's why. So 1160, 11,600 is my intensity needed to kill 90%. I'm on this one. Bacillus subtilis spores. The difference between the spores and the actual thing, I don't know. But I just picked one randomly. So divided by 800, I need 14.5 seconds of shine time to kill those guys effectively. Pick something else. I picked influenza. Let's say I want to kill 99% of influenza. I need 6,600. You notice the viruses in general are easier to kill than most of the bacteria. Viruses are apparently wimpier. I don't know. But I need 6,600. Divide that by the bulb intensity. I need 8 seconds of shine time. If I'm moving air at 500 feet per minute through my air handler, assuming I'm putting the bulbs in my air handler, that means I'm moving at 8 feet per second. That means if I do the math out and I separate these bulbs by 1 foot, because that's what they're rated at, 1 foot is that intensity, I would need a bulb every 2 feet. So bulb shining 1 foot, bulb over here shining 1 foot the other way. I need a bulb every 2 feet for 66 feet of length. If you're a bulb salesman, this would be fantastic, but nobody's going to want to mount that. Plus, when I get down into the duct system, I'm no longer moving at 500 feet per minute. When I first exit the air handler, I'm probably moving at 1,800 or 2,200 feet per minute. And then as I go through the duct system, I'll be moving a little bit slower. But the only place I'm moving at 500 is the filter and the coil. Everything else is moving faster. So I would need even more. If you want to look at COVID specifically, this wasn't in these charts because these charts predate SARS-CoV-2. But I found some examples from one of the universities. Actually, I stole this from the guys at Sterile Air who found some examples from universities. We don't rep Sterile Air, but I credit them because I stole from them. But here it tells you the actual source. So this here, 10% means 10% of the virus survived, meaning you killed 90%, you killed 99, you killed 99.9. So if I want to kill 99.9% of the SARS-CoV-2 virus coming by the UV bulb, I would only need 2730. It's like super wimpy. It's wimpier than any other virus. It's literally the wimpiest virus I could ever find. I know that's not what you want to hear after isolating yourself for 2 years, but it's super easy to kill it with UV light if you can get the UV light on the virus, right? So I do the same math on that guy, 2,700 divided by 800. I would need 3.5 seconds of shine time. That means I still need 28 feet worth of bulbs spaced out every 2 feet. That's not practical. Now, if I'm a UV bulb salesman, what I would say to you is like Ryan, I mean, come on, man. It's going to go through the air handler. I'm going to get 1 second of shine time. Then it's going to come back around through the building, come back to the return duct and come again, and I'll get another second. And after enough time, I'm going to get the full 4 seconds and I'll get it all. Maybe. It's true. He's not lying. If you get 1 second now and 1 second later and 1 second later, it is additive. Just like if I go out in the sun for 2 hours and get a little bit burned up, go inside for 10 minutes, go back outside, the clock doesn't start over. The clock starts on the 2-hour mark, right? It resumes where it picked up off in terms of burning my skin. Same thing is going to happen here. But what are the chances of that virus going around the building 3-4 times? We already explained how difficult it is to get the virus entrapped in the air to begin with. If I got it to the UV light once, I'm already feeling like I did pretty good. Chance of doing it multiple times is pretty low. So it is what it is there. You're not going to be killing germs in your building with a UV light mounted in your air handler. You're just not. You'll kill some, granted, but it's not enough that it makes it interesting in any way by itself. So what the hell is the UV light for? The really good benefit of the UV light is killing germs on something that's stationary, not moving, not the air, but maybe my coil. My coil has crap growing on it. If I shine a UV light on my coil, crap's not going to grow on it. Same with my drain pan. That's what it's for, keeping my coil clean. I'm not the only one saying this. ASHRAE is saying this as well. I stole this from Carrier, but they're quoting ASHRAE. ASHRAE writes, the control of a moving airstream does not provide favorable killing rates with UV light, that's the article, because of the short dwell time. Will it kill stuff? Yeah. Will it kill a good amount of it? No. It's moving too fast. right? Some of those germs are going to run into the light bulb. They're going to get killed. Some of them are not. They're going to get by scot-free. It's really good at reducing biological growth on your coil. That's what it's for. Now, there are UV lights you put in the room called upper room UV lights, and those are a little bit better at killing germs in the room because the light bulb's in the room. But that's not for HVAC, so it's off the table for our discussion today. We're talking about HVAC solutions here today. But you could do that in the room and help out a little bit. If you're going to put them in your air handler, where should you put them? The best place is to put them by the coil, because that's literally the only thing they're going to do a good job of cleaning. And they're going to do a really good job of that, but they got to be by the coil. Personally, on a horizontal airflow path like this, I like them after the cooling coil, because my drain pan usually goes from here to there. So now they shine on my coil and on my drain pan. If I had like a residential house with an A coil and an upflow furnace, I would put it on the inlet side of the coil, because that's where the drain pan would be. But on an air handler in a commercial building, downstream of the coil, because then I get the coil and the drain pan with some shine time. So it's going to not only keep my coil clean, it can actually clean my coil. Technically, I could put the UV bulbs on these guys on a dirty coil, and after X amount of time, the coil would be clean again. Two problems with that. One, the customer that just paid you to put those bulbs on there doesn't want to wait 6 months for the coil to get clean. They kind of want it to be clean now. So really, you should clean it manually with coil cleaner and then put the bulb on to keep it clean. That would be smarter. The other problem is if you just do the bulb on there and it kills the crap on the coil, then as the coil heats up and cools down, things expand and it's going to flake the debris off the coil and it's going to fall into the drain pan and it's going to clog up your drain. So you really need to clean this crap off manually the first time, and then the UV light's job is to keep coils clean. That's all he does. Keeps coils clean. That's his job in life. How many you need and where you need to put them is a function of where you're going to locate them and your bulb manufacturer's spec. The shorter the distance, the more likely you can get away with one bulb. As it gets taller and taller and taller, you probably need more and more bulbs, or you got to put the bulb further back, and you may or may not have space to do that. It just depends. In addition to keeping the coil clean, germs are gross. It helps out with two other things. Heat transfer. If I have to cool down my coil, to cool down my fan, to cool down my debris, and then my debris actually cools the air, that's another layer of insulation, if you will, and that takes longer to cool with. And then airflow wise, if there's things on my coil, it restricts airflow as well. So the combination of heat transfer and airflow ends up being pretty substantial. This was out of a healthcare engineering journal from California. So who cares about California other than it was a nice piece of information. It's not new science at all. This is old stuff. But the more thick debris you have on there, the bigger and bigger energy efficiency loss you're going to have from both airflow and heat transfer. And then also stolen from our competitor at Sterile Air. Give them credit because I stole from them. But they got a couple quick slides on here that just shows you improvement of pressure drop across the coil by having UV light cleaning it, improvement in airflow, improvement in dry and wet bulb temperature control. Lots of benefits to keeping the coil clean, other than just not having something gross on your coil. All right, quiz question number 4. Once again, if you're playing along for PDHs, you need to answer these correctly. Which item are HVAC mounted UVC lights the most effective at cleaning? Your choices are supply air, room air, cooling coil surface, room surfaces. Which one are they most effective? I'm just going to tell you right now, they will kill things on all of them to a degree. Well, they'll kill things they'll kill things on 2 of them for a degree if it's HVAC mounted. But one of them, it'll kill way better than others. And by the way, our company sells UVC lights, so it's not like I'm saying anything to pick on UVC lights. They have a purpose. Keep coils. I almost give you the answer. They have a purpose. If you don't get the answer now, I swear. All right, I'm going to close it in 10 seconds because you got the answer. 8, 7, 6, 5. Answer. Quickly answer. Closing it. All right. That one was a softball one. 94% of you got it correct. Cooling coil surface area is the most effective. You could make a slight argument for killing germs coming to your supply air. You could not make an argument for cleaning the room air because it can't even shine on the room air. Although eventually the room air comes into the return air, which becomes the supply air, so I guess you can make a slight argument there. But definitely nothing on room surfaces. Cooling coil surface is where the action is at. All right, moving along. There are some other technologies in the marketplace that have UV lights in them, but they are not UV lights per se. Damn it, I got an hour of stuff to do in 35 minutes. I'm going to go fast. So that technology, typically it's PCO. Sometimes there's also carbon and other things going on. We'll explain that. So some of the widgets look like these things. PCO stands for photo, catalytic, oxidation. Photo means there's light involved, hence the UV light bulb. Catalytic, something that causes a chemical reaction. And oxidation, the result of this process is I'm going to make oxidizers. Photocatalytic oxidation. So let's go through the steps on how this thing works. One, there's a UV light in there. Some of these devices, this one up here in the top left, it's got some titanium dioxide plates on top, carbon plates on the side, and the bottom in this example is open. There's nothing on it. And this would be for this example that I'm telling you about would be an upflow coil like that. So the UV light is shining down on that coil to a degree. It does help keep the coil clean if you have that type of configuration, right? So we'll skip the coil cleaning lecture. We already talked about that, so you kind of get that. The other thing is that some of these devices, not all, but some of them have carbon cartridges on the side. Little honeycombs on them that airflow can move through. And the UV light bulb's inside there. He shines on that carbon to regenerate it. The carbon is there to absorb odors. Some of you that have done commercial applications may have put carbon filtration on something. There was an air handler at one of the hospitals on the south side where the intake for the air handler was next to the helipad. So 2-3 times a day, a helicopter sat there for 15 minutes spewing diesel fumes into the air that was getting sucked into the outside air intake. They put carbon filters on there to absorb those diesel fumes to help out with that situation. Apparently that was easier than relocating the intake. Carbon's really good at absorbing odors and chemicals. It does have to be changed out. Putting a UV light on there regenerates it so it can last longer and not have to be changed out. It says never. I don't know if after 20 years you might want to do it or something, but that regenerates it so it lasts longer. Right, carbon's good at absorbing odors. We said that. The last thing is that white plate on top of this particular one we're showing is a very similar plate to the carbon cartridges, but it's not carbon. It's titanium dioxide. So in this case, titanium dioxide is going to be what causes my catalytic reaction. When I shine UVV or UVC light on titanium dioxide, it creates oxidizers. Specifically, it creates hydroxyl radicals. Hydroxyl means there's hydrogen. Oxyl means there's oxygen in the discussion here. Radical is what I want to focus on. Radical means it's not stable. If you flash back to high school chemistry, if you loved it as much as I did not love it. And I liked college chemistry even less, which is why I went into HVAC to avoid more chemistry in my life. But radicals are unstable things. They're very reactive. They don't want to be radicals. Everything in the universe is trying to get to this magical equilibrium. These guys, somehow they know that, and they want to be more stable. So they will react with other stuff that they interact with and become more stable things. So I'm creating these hydroxyl radicals, sending them out into the space so they can attach themselves and or rip components off of VOCs and other things that are floating around in the air. So I'll look at one example here. Get my laser pointer thing figured out again. I got this UV bulb right here. He's shining on one of these titanium dioxide plates. That's creating oxidizers. In this example, he's actually going to create 3 oxidizers, but we're just showing one of them here, OH positive. It could be a negative. I can't even squint and see that smallness on my vision here on my little cube. And those guys are going to be going out and they're going to be breaking down chemical compounds. Also, because they are charged, they can clump around stuff, just like the secure air thing or other stuff we were talking about earlier. They can clump around stuff and have an effect on those. They'll surround those guys. We'll talk about how they inactivate germs here. But essentially, as they surround them, the germs cannot get anything else coming in, like nitrogen. Most germs need nitrogen to survive, just like you need oxygen to survive. They need nitrogen. If they're surrounded by a bunch of other crap clumped around them, they can't get very much nitrogen, and they die off. Additionally, once they're on there, instead of a certain mass of this clump, it's a much bigger mass. Once it's a bigger mass, it's more likely to get sucked into the airflow path and make their way back to the filter at some point. Most of these PCO devices are creating 3 oxidizers. This is just showing an example of one of those. This is some test data on an oxidizer, not one that we use anymore. It's a brand we used to handle, but I'll show you some other ones we do handle now. But most manufacturers will test at least 1 bacteria, at least 1 virus, at least 1 mold, and have some third-party testing on that to show you the inactivation rates of those things. And then The bigger companies will test more than one because they can afford the testing. Smaller companies probably can't. We tend to use a lot of stuff from Respicare. I want to say we switched to them 8 years ago. We switched to them for numerous reasons. One of the reasons was they made a lot of stuff. So we get our UV lights from them. We get our PCO devices from them. We get this Oxy 4 device from them, which I'll explain. We get some bipolar ionizers from them, which I'll explain. So lots of stuff going on from one manufacturer. And as a distributor, if we can have one supplier instead of 3 suppliers of 3 different things, it makes our life easier. So that's one of the main reasons we switched to them. The other thing is this Oxy 4 thing. We were excited about that. Oxy 4, the 4 means there's 4 oxidizers. Write that down. There's 4 oxidizers. 3 of the same are what we have with PCO, hydroperoxides. And just by the name of that, you can tell what that's going to be, right? Hydrogen peroxide, brown bottle, pour it on the cut. When you're a little kid, scream like a baby, but yet your germ is cleaned out, right? Your wound is cleaned out. It creates those in the air. Superoxide ions, hydroxide ions. It's creating these 3 oxidizers, which like to go attach themselves to things or neutralize things. Then it makes a third one. They call it oxidizing ion, O3, and in this case, negative charge. This oxidizing ion, O3, that's ozone. It's creating ozone and using it as a germ-killing agent. It's really effective at doing that. Some people don't want ozone in their life. So for some customers, this is not a good solution. You might just stick with a regular PCO device because they don't want any ozone in their area. Now, you can follow the rules for ozone from FDA, for example. FDA is the most restrictive, I believe, and I want to say it's like 5 parts per billion. I forget what it is off the top of my head. But if you size this correctly for your space, you can keep it underneath that limit and be fine with both OSHA and FDA requirements. Or you can do stupid stuff and put a giant commercial one in a small space and, possibly produce too many that can't be utilized. But some people are nervous about it. They don't want any of them. That's fine. You don't give them that. You give them a regular PCO device. But just know in your head, of all 4 of these oxidizers, this oxidizing ion, that's the most powerful one. So if you're more concerned about germ killing, you probably want to go this route. I have this in my house. I'm doing it. I've been doing it in my house for 7 or 8 years now. Before that, I had a different product that created mostly hydroperoxide ions. I was also happy with that, but this has been pretty cool. Just as a side discussion, when I first put it in, it didn't do much. Like the old one I put in, I'll say 13 years ago now, the old brand, it was fantastic, dude. We had 2 kids at the time. I put this thing in. They're both in preschool. Preschool is where your kids go to share germs. They like lick toys and hand them to each other and stuff. So we'd have a kid that would go to school. Somebody at school would get them sick. They'd come home. They'd get the other kids sick. They'd get us sick, whatever. Once we put this in our house, or not this, but the one I had before this, put in our house, nobody got sick at my house. It was a 3-year bulb in that thing. I swear, 3 straight years, 36 months of none of my kids getting anybody else in my house sick. And then finally, one of my kids got my other one sick. And my wife's like, I think your little bug zapper, she does this to piss me off with her fingers, your little bug zapper isn't working. I'm like, what are you talking about? She's like, that thing you put in the duct downstairs. I'm like, that thing's great. It's been great for like 3 years. Oh, 3 years. Shit, I got to change the bulb. Went down there. Sure enough, the bulb was burnt out. Put a new bulb in. Another 3 years of nobody getting sick. And at that point, I had 4 kids. Nobody got anybody sick. It was fantastic. Then we switched to this other brand, Respicare. And they wanted me to put it in. My office did. And I'm like, dude, I got another one. The old brand. It's working great. I'm happy. Like, yeah, we don't sell that anymore. I'm like, yeah, I could still just put it in anyway. I don't care. Or I'll just get new bulbs for it. They wanted me to put this in. They finally talked me into it. I put it in. And then my kids got sick from each other. I was like, what the hell? So I called up Respicare. I was all bitchy and whiny about it. And they're like, maybe it's defective. We'll send you a new thing. They sent me a new one. I put it in. Kids still got sick from each other. I was like, dude, your product sucks. It's horrific. I don't like it. So then they sent me another one, the big commercial one, the 16-inch one. Like, just try it, right? Instead of 7 inches, they gave me the 16-inch one, which puts out a boatload of oxidizers. And still, it was not very effective. And I'm like, dude, this is crap. I'm going back to the old one. And then finally the lady says to me, well, you rotated the clips, right? I'm like, what are you talking about? What clips? She goes, in the instruction manual, like page 3, it says you got to open it up, and there's these metal clips that block off 75% of the light output. And if you want more light output, you got to spin the clips. I'm like, I did not read the instructions. So I didn't read the instructions. I'm like, of course I didn't read the instructions. I'm a dude. We don't read instructions. I just shoved it in the duct, man, and plugged it in. So I went and rotated those clips, and actually then I peeled the clips off completely. So I have 100% bulb output. I've never looked back since. In fact, I went back down to the 7-inch one with no clips on it. It's been fantastic. So just a little side story there. But this stuff works. Like literally, I know it's anecdotal, but at my own house, it's been working for us for a long time now. It's been great. Just got to change the bulb every year on them. If you get to larger commercial installations, you can piggyback one off the other and share a power connection. You can tandem 2 of them together. You could also put like 4 of them in and have 2 off of one power supply and 2 off the other. At some point, putting in a bunch of these, like you want to, put in like, 10 of them to handle like 25,000 CFM. At some point, it's getting a little ridiculous. And we have other technologies that we'd use. But 1 or 2 of these guys together, 2 of them together handles a 20-ton unit. So that's pretty decent size. That handles, 70% of the air handlers and rooftops that we'd interact with. And then when we get stuff bigger than that, we're going to go a different route. And I'll show you the different route options here in a minute. The other nice thing about this Respicare brand is they're one of our suppliers that got all their stuff, I shouldn't say all their stuff, all their major stuff tested for SARS-CoV-2. They got 99% reduction rate in that COVID-19. So that has been beneficial. Obviously, from a marketing standpoint, people ask if you can deal with SARS-CoV-2. And if you say, yeah, it probably works, that's not as effective as saying, yeah, we have third-party test data that prove that it works. So that testing came out, I want to say, I'm going to guess, September or October of 2020. So it's been a little bit while now. Other than killing germs and obviously SARS-CoV-2, it's good for places with odors, places with people that have lower immune systems, nursing homes, daycare, etc. So those places are good. It does help kill stuff in the space. It's not killing germs on a coil like a UV light. It's not capturing germs at the air handler like a filter. It's actively sending oxidizers down your duct and out the diffuser, and it's landing on your desk and your counter and the toys of the daycare. It's actively killing stuff in the space. So even if you put a good filter in, like in my house, I have a Merv 15 filtration system in my house, and I still have this on there. It's a fantastic combination of things. And it's not that cost prohibitive in the grand scheme of things, but it's active. My filter has to wait for something to show up at the door, and then it can catch it. This guy goes out in the space and kills stuff in the space or inactivates it in the space. All right, quiz question number 5 out of 8 questions. How many oxidizers does Oxy 4 produce? Another softball question. All right, I'm going to close it in 5 seconds because most of you guys answered. 5, 4, 3, 2, 1. Okay, excellent. You guys all got it right. That hardly ever happens, right? And it's easy. It has a number 4 in the actual word of the product. So 4 oxidizers is correct. By the way, if you ever needed to, let's say you got one of these Oxy 4s for a customer, you put it in, and then later on they read some article and said, oh, I heard ozone's not great for you. And you're like, yeah, but we're going to be under the FDA limit, blah, blah, blah. No, dude, I don't want any ozone at all. I want 0, bro, 0. What you could do is you can actually swap this bulb out. It comes with a UVV bulb. If you call Respicare and say, hey, I got this customer concerned about ozone, blah, 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 they will send you a UVC bulb that fits in that socket and effectively makes it an Oxy 3. They don't call it that, but we jokingly call it that at the office. So you could dumb it down later if you want to. In fact, there's enough people that have asked for that. They made a new product, which is essentially an Oxy 3. They call it Oxy X because that's probably more marketable. It sounds like, kind of like when iPhone skipped the iPhone 9, they went to iPhone X. I don't know why they just did. The X makes it more marketable. I don't know. So they call it Oxy X, but it's basically 3 oxidizers instead of 4 because it has a UVC instead of a UVV bulb. That's just a side note. All right, moving on. Bipolar ionization. Let's talk about that. That's another way we can actively kill germs or quote unquote inactivate germs in the space. Instead of waiting for something to show up at the door, we can deal with it in the rooms, just like the oxidizers we were talking about. So you saw we were creating oxidizing ions over here. Somewhere on the slide it said the word ions, right? Oxidizing ions, same kind of thing. We're going to create ions, which are the things that are going to be actively helping us in the space. Ions occur naturally. Waterfalls being a very common example of that. Water flowing through the air creates ions, a lot of them, 5,000 to 20,000. A lot of them can be created that way. So we're going to naturally create them in the world, and now we're going to intentionally create them in our air handling systems to help us with that cleaning ability. Ionization is not new. This is old stuff, dude. Like, this article is 10 years older than me, and I'm old. So this is not new stuff. Back then they were using it for capture, but we're also going to use it nowadays for killing stuff. So there's more articles in this. It's just the oldest one I could find. In fact, the ASHRAE Journal last month, 2 months ago, trying to think, had a pretty good article on ionization for indoor air quality reasons. But this one was for catching dust and debris and for controlling static electricity in buildings, was this article's original purpose. All right, so the bipolar ionization. Bipolar, bi means I got two, so I'm gonna have two poles here involved, and I'm gonna be creating ions. We're specifically gonna be focused on needle point bipolar ionization, so that gets an acronym of NPBI when you see that on stuff. Needle point means I'm using little tiny needles to create it. I'll show you some pictures of what that looks like. These ions, similar to the oxidizing ions we created with the light system, these ions are going to also be able to break down chemicals and attack single cell organisms and break down their DNA, very similar to what the UV light was doing. So kind of a similar concept going on. The one nice thing about this is we can make some controllability of it. And in order for these ions that we're creating, they can be specifically set up for a certain electron voltage. And the ones that you find in the field nowadays are 12 electron volts and lower, meaning anything less than them, they'll be able to break those chemical bonds. And anything more than 12 electron volts, they cannot break down. So they cannot break down oxygen, which is O2. That's on purpose. They designed them for 12, so they can't break down 12.07, because if they did, those two oxygens would be separated by these ions. And then they might regroup as two O's together, which is regular oxygen you breathe, or they can regroup in clumps of three, O3, which is ozone again. So in order to make sure these don't produce ozone, they set them at 12 electron volts, and then it's impossible for them to be ozone producers. Some of the older style ones, and even some of the low-end ones you could probably find in the market, can produce ozone. So if you're going to do one of these, make sure you buy one that's certified not to produce ozone. We'll talk about certifying in a minute. So this is basically what's happening. These ions are created by the bipolar ionizer, and they make this plasma field of ions. When chemical compounds pass through that field, it breaks them down. This is ammonia in this example, which is 3 parts hydrogen, 1 part nitrogen. Hydrogen and nitrogen are not harmful to you. When you combine them in this combo, it's ammonia, and then it is harmful for you to breathe. It busts them apart. They could regroup as ammonia. That's possible, but it's not likely because ammonia is fairly complex. They're more likely to combine as non-complex things. For example, 2 hydrogens can jump on an oxygen. That creates H2O, water vapor, pretty safe there. 2 of the nitrogens could jump together. That creates N2. N2 is the regular nitrogen that comprises, like, I forget, 79% of the air you breathe in the atmosphere. Pretty benign stuff. That's his job in life. Take a complex thing, bust it apart, and then let it combine back as not complex things that are involved in your everyday life, and hence more safe. The other thing that's going to happen is because there's charges associated with these ions, they're going to be able to cluster and clump onto stuff. Just like with the oxidizing ions we produced with the PCO style devices and with the Oxy-4, we're creating hydroxyls, hydrogen and oxygen based things, natural detergents. Speaking of which, if you ever buy like Tide with Oxy, you know, the orange bottle of Tide for your laundry, Tide, and it says with Oxy is one of the kinds they have. Those are oxidizers. They're putting oxidizers in the laundry detergent to kill germs on your clothing. At my house, we don't have it anymore, but we beta tested for Gas Technology Institute. My wife and I, well, she said yes, and then I had him do it. She says yes to things sometimes. I had him install on my incoming water line to my washing machine an oxidizer. It created oxidizers and injected it in the water. And for that, whatever it was, I forget, 18 months or whatever that test was, we didn't buy laundry detergent. We just stopped buying it. And the oxidizers were our detergent. It was fantastic. Clothes smelled great. Things were clean. We didn't spend any money on laundry detergent. It was awesome. The water was just like pre-detergent by the oxidizer. But then the study was over and they collected their stuff back, and that was that. You can still get those for like commercial laundry systems, but I haven't seen any for residential usage yet. I'm hoping that eventually comes out because it was pretty cool. In any case, those oxidizers are natural detergents and they can attack germs and break things down like we talked about. And kind of like the other one we talked about, when they clump around stuff, they deprive them of the oxygen they need to survive. Excuse me, the hydrogen they need to survive. You need oxygen, they need hydrogen. So it'll deprive them of that and neutralize them. This chart is actually pretty cool. It's probably the coolest chart in this slide presentation as far as cool charts go. Here, this is actually a little bit older. This is pre-COVID stuff. So when it says SARS on here, it's not SARS-CoV-2. It's the original SARS, which sounds so stupid to say that, but that's what it is. But it's similar size particle to the current SARS. So we'll draw some conclusions. But there's a Merv rating from specific filters. And then they had a HEPA, which is not technically Merv rated, but it's kind of like having a Merv 17 or better. And this is how much of that size particle those things were catching as it went through, right? So a Merv 10 was catching 12%, a Merv 15, 71, 99. This is kind of how ASHRAE came up with that Merv 15 or Merv 14 recommendation to summer and a half ago for COVID, because that got them a little bit better than 50% capture rate on the COVID viruses that made their way back to the filter. And they said if you can't get a Merv 14 to fit, then you can go ahead and do a Merv 13. It's not bad. Anything less than a Merv 13 is pretty worthless for catching this stuff this size. If you were to combine a Merv filter with a UVC light, then how much are you capturing and or killing? You can see you get a pretty good bump. So you shine a UV light on your filter, which seems kind of hokey because you kind of already caught most of that stuff. So to kill it on the filter is slightly less exciting, but it does have appreciable benefit. I mean, instead of 46% capture, you're getting 84% capture and kill rate on that thing, right? For a HEPA filter, it's not exciting because you already captured most of it. So killing a couple little more bits is not really that much interesting to me. If you combine it with an ionizer instead of a UV light, it's an even better jump. Your Merv 10, 12% by itself, 35% with a UV light, 89% with an ionizer combined with it. Merv 13, I'm basically getting 98.8. I'm getting almost a Merv performance out of a Merv 13 when I combine it with an ionizer. So we've been doing that fairly frequently. A Merv 13 is kind of about the best we can stick into like a rooftop unit, but it's really easy to put an ionizer in there. So I can get almost Merv benefit, at least as far as viruses are concerned, out of a Merv 13 plus ionizer combo. So that's an option to think about. This is from an EPA document. There's also some stuff from a couple of different labs that ASHRAE cited in one of their presentations. I literally screenshot this because I am lazy and cheap. But those two studies, one took Merv 8s and combined them with needlepoint bipolar ionization and got Merv 13 performance. The other one took a Merv 12 and got Merv 14 performance. So they're getting 4 to 5 Merv points better. The higher you start out on the Merv rating, the less extra benefit you're going to get, right? Kind of like this, like, well, you already got almost everything. Like, how much better will an ionizer get you? Will it help? Yeah. Will it help as much as it would by putting it on a mediocre filter? No, because a mediocre filter sucks so bad. There's a lot of room for the ionizer to benefit it. Whereas a good filter is kind of already good, so you can only make it a little bit better. Some of the key to these ionizers is getting the ions in the space. The ionizers create the ions. I need to deliver them to the space. They don't last long, like a minute. You create an ion with an electrical device, it lasts about a minute. And by then it's already combined and knocked around with other stuff and they're pretty much used up. So I need to use them within that first minute or less. A minute's kind of like the cap. So I need to get them close to the space. On a small system like at your house, put an ionizer in your furnace, and the air from your furnace fan will be delivered to your rooms in under a minute. You're kind of good. On a big system with long ductwork, putting the ionizing device in the air handler, mixed results there. It does a good job of killing stuff on my coil because the coil is right there, but it doesn't do as great of a job in this space because they get used up. So in a really big building, like a multi-story building, you got 10 floors of a building, I may want to put a duct-mounted one on each floor and let him take care of that floor versus putting one back at the air handler, and then the chance of him getting from the penthouse all the way down to the first floor and still having ions left is kind of hard. So I may choose to do some duct-mounted ones instead. One of the companies we've been using for a long time is GPS. We used them for years and years and years. Then we stopped using them and kind of focused on the respiratory stuff. And then what would have been September 2020, they came to us and said, hey, our current rep is not doing a good job. Would you like to distribute the product again? And I don't know how they weren't doing a good job in the middle of COVID. I don't understand that at all. So, and we were at that point, we're selling every single respiratory thing we could get on the shelf, literally like people would buy the wrong size just to get something. So we're like, yeah, we could take on another IAQ line. Absolutely. So we took it back on, and now it's by far our largest IAQ line in terms of sales dollar volume. It's huge. In fact, it's one of our bigger brands in general, not just IAQ. It's massive amount of stuff that's been moving through our buildings, going to customers. They make all kinds of widgets. They used to only make a small residential thing and then a large custom built commercial thing, which made it hard for us because a custom built thing takes a while, obviously, because it's custom. So you can't sell it quickly. Whereas now they have all kinds of everything in between. So we'll talk about a couple of these real quick. They make ones that mount just about everywhere. The common ones are this FC24 and 48. I should mention real quick too. They make a little tiny one that you can use residentially. We don't use a lot of them residentially. We tend to use the respiratory care stuff, but they do make that. But for commercial stuff, the FC24 handles 24,000 CF or 2,400 CFM, which is a 6-ton unit. The 48 handles a 12-ton unit, 4,800 CFM. Right? They're very similar. They both mount on the unit. They can be mounted by screwing it in or a magnet, either way. Right? These large magnets that go on here. And then they both have a way of keeping the needles clean. This one's got this little like windshield wiper, bipolar. So 1, 2 sets of needles. These are needle point. So I have all these little carbon needles on here. And then once a day, this wiper goes swish, swish, and knocks any debris off it. You don't want debris, dust, to build up on the needles because then it can't cause that electrical reaction because it's getting basically blocked by the dust. So you got to clean the needles off periodically. You don't have to do it daily, but this product just does it on a daily basis. Swish, swish. This one's got more of a helicopter thing, but it rotates and knocks both of them off, and away you go. Installation is really easy. If you get one of these, let me know. I'll send you a video on how to install it. You'll notice that on these slides too, on all of them, it says UL 2998 ozone free. These do not produce ozone. They're UL tested for that. I'll explain that UL rating in a minute, but all of these guys are tested for that, which if someone cares about ozone, you're going to want to fixate on that concept. If you have a bigger building and you want to put them down the duct, there's a duct mounted version of this that slides into the duct. So this whole piece would be stuck into the duct. So it's a duct mounted version. The more ions these guys produce, the more effective they are. So these guys are producing the same amount of ions, but this one just a different mounting configuration than that one, right? And then the smaller one produces less ions, but it's going on a smaller system, so I don't need as much, right? And then there's the really small stuff that doesn't produce hardly any, but it fits in little tight places, like maybe a unit ventilator or a fan coil, something like that. And then they make ones that fit in really small spaces, like PTAX at a hotel or ductless mini split heads. It's a ribbon that rolls out, and there's little. Now this one's not self-cleaning. There's no wipers on it, but there's little bipolar ionizers every 3-4 inches that just kind of sit on top of this coil. And then there's a little box here that's smaller than a deck of cards, and it fits in the side over here. They make the opposite of that. They make a really big one. Like I said, we used to have to get custom stuff made for large air handlers. Now it's not. Now what they have is a modular one. There's a power supply box and the first 6 inches, and then you just tell them how many more 6-inch pieces you want, and you just clip them on there and make any length that you want to cover the whole length of the air handler. This works best when we're doing it for coil cleaning purposes. So instead of a UV bulb downstream of my coil, shining on my coil and my drain pan, I would have ionizers upstream of my coil, and the ions are getting mostly consumed by things that are growing on this coil. So after enough time of this guy running, this coil will get cleaner and cleaner and cleaner. Although once again, you should clean the coil manually instead of leaving it dirty. So if you're concerned about coil cleaning, this is a good configuration. If you're more concerned about space cleaning, you probably don't want this. Instead, you want to put ones that are downstream in the duct like we showed over here, closer to the space. So it depends on what your goal is. GPS was the first manufacturer of any HVAC stuff that we're aware of to get tested for SARS-CoV-2. This was in June of 2020. So like 3 months after the crap hit the fan in March, they already had stuff tested. That's mainly because they have an aviation group. And I think one of the big aviation manufacturers was able to get their hands on some of this virus. In order to test stuff, you have to get the virus. And so you need a lab that has that. And that wasn't readily available. Those labs were doing non-HVAC things at the time with COVID. But the airline people are big. They got a lot of money. So they're able to get their stuff tested. And they use GPS products at the airline. So GPS said, hey, can you just throw some of our other stuff in the test and test that while you're testing the aviation versions? So they were able to get their stuff shown that inactivates SARS-CoV-2 really quickly at a 99.4% rate, which is fantastic. I think the original testing was actually 99.4, and some of the more recent testing was 99.9. To me, that's the same number, but nonetheless. And obviously, it's been tested for all kinds of other germs as well. So we got that going on. I threw this in here just so you have it. If you want these slides, I can send them to you. Just email me later, and I'll send them to you. We got to wrap up in a couple minutes here. But the CDC position, the ASHRAE position as relative to the CDC on some of these kinds of things. The long story short is ASHRAE, like anything else, doesn't make recommendations for specific products, but they're telling you if you're going to use things like air purification, bipolar ionizer, stuff like that, you should make sure you have one that's UL 2998 listed. And since then, they believe in that so much that in the latest version of ASHRAE 62.1, they actually require that all air purification be UL 2998 listed. That's kind of the concern with most of the people at ASHRAE with recommending certain types of products that will, yeah, it kills germs really well, but if it's producing too much ozone, that's a problem. So the UL standard resolves that. So when you kind of read that, it'll kind of fixate on that. Most air purifiers have always been UL tested, but they're tested to UL 867. 867 does have an ozone test, but only for portable air cleaners, not for permanently mounted stuff that you'd find in HVAC. So, and even the portable ones allow 50 parts per billion, which is relatively high. It does not meet the EPA requirement, or OSHA for that matter. So the new standard UL 2998 is more restrictive and is required for all air purifiers, not just portable ones, but even permanently mounted ones. And you got to be under 5 parts per billion instead of 50 to basically say you're zero ozone. So zero ozone really means 0 through 5. It's required by ASHRAE now, and it's required for everything: UV lights, electrically powered filters, ionizers, PCO devices, everything would have to follow the same rules. I'm going to skip some slides in the interest of time here because I've gone long. But if you're interested in GPS technology, it's not new either. It's been installed in many of the healthcare facilities and other high-profile places, universities and stuff like that. So it's not new in any way. It's just that the past 2 years I've been using it for COVID projects instead of just other things that they're trying to kill. But it's kind of non-discriminatory. It inactivates all kinds of germs. It doesn't really care. Respicare's got a small ionizer for residential as well. We use that sometimes. As I told you before, we use Respicare for all kinds of stuff: UV lights, PCO devices, Oxy-4, ionizers, filtration, a whole bunch of stuff, mainly light commercial, residential. And then we'll use Secure Air and GPS on the really heavy commercial stuff because it's more scalable. But there's solutions for everything. Any solution you get from us or somebody else, they should be able to produce for you third-party test data tested by somebody, whatever, Kansas State University, so-and-so labs or whatever, showing their inactivation rates of various kinds of germs that you might be interested in knowing about. Not just COVID, but other stuff too: bacteria, mold, viruses, etc. I'm going to skip these slides in the interest of time. Just know there's a bunch of labs out there testing a lot of this stuff. Okay, there's a lot for Respicare apparently. All right, last couple things. I'm going to skip some of these. Duct smoke detection, carbon monoxide detection. I think you guys get that stuff. I can have a whole separate discussion with you guys on that. I didn't prepare any slides for them. Those are important things. If you have things that produce refrigerant or could leak refrigerant or produce carbon monoxide, you should be able to have sensors in there to alarm people. Ventilation air we already talked about. And that really leaves the last topic of humidification and dehumidification. It has an effect on things like viruses, and actually it's a fairly substantial effect. You've all seen this chart. This is out of the ASHRAE handbook. It's called the Sterling chart because some dude with the name Sterling first put the chart out. You've seen it in numerous versions that are prettier than this, but it pretty much always says the same thing. If you keep things between 30 and 60%, less bad stuff happens. Sometimes you'll see it referenced as 40 to 60% to minimize the bad things. Less bacteria, less viruses. If things get really dry, certain viruses thrive. If things get really hot, humid, certain viruses and bacteria thrive. If things get humid, mold and fungus thrives, right? Keep things in the middle, less bad stuff happens. There's numerous slides I can use to try to explain that. They're fairly complicated and they're always in Celsius for some reason. So I got to go put Fahrenheit on the side. Otherwise, I won't know what the hell's going on because I only memorized 1 Celsius number. Actually 3. 0, 25, and 100. But these curves here are telling you the likelihood of influenza to survive at various humidity levels. If it's 86 degrees, right, I'm going to pretty much get rid of all influenza. It doesn't survive very well above 86%. It's pretty much almost zero survival rate unless it gets really humid, right? Each one of these guys, you see where they're dipping down on these curves. They're dipping down between that 40 and 60% sweet spot. So 50% survival of the virus is this black line right here, that black line. If it's 20% humidity, 77 degrees it would survive, right? But it's 77 degrees and 40%, similar. 77 degrees and 50%, a lot less survives. Right now I'm down to this dotted line, 25%, even between there, maybe 20%, right? In between those two lines. So if I keep things between 40 and 60% at almost any temperature, less bad crap happens. A couple other studies that are similar, also unfortunately in Celsius. I'll just do one of them for now. This is showing you cold temperature, medium temperature, hot temperature. Obviously, the 68-degree curve is the most similar to what you keep a building at. And once again, between 40 and 60%, the least amount of the virus survives. Virus survives 100% up here. 10% survival rate, meaning 90% inactive, 99% inactive, right? 1% survival rate. So if I keep between 40 and 60, the least amount of viruses are going to survive. All right, quiz question number 6, so we can get you guys out the door. And we got one more after that. True or false, maintaining indoor spaces between 55 and 75% relative humidity is best for minimizing bacteria, virus, and mold. Oh, dude, I just clicked off of it. Hopefully it popped back up. I had to click twice on accident. So is that the sweet spot? Is basically the question. Are you guys able to answer it and click on it? So apparently me clicking it twice really fast disabled the question. All right, let me try it one more time. This one. Yeah. So I'm dumb. So here's the good news. The good news is I clicked the button so fast in a hurry that I effed this up. So the good news is you all have it right. I'm going to go in and artificially change your answer. The answer is false. That is not the sweet spot. The sweet spot would be 40 to 60%. If you're above 60%, bad crap happens. We mentioned it a couple minutes ago. And we also mentioned it early on where I want to keep things below 60% for comfort and 65% and below for mold growth reasons. So the answer is false on this, is not the sweet spot. But nonetheless. All right, last quiz question, and I will not click it too fast. This is our last thing for the day because we're already at noon. Remind me again if you need a PDH certificate. There's no wrong answer here, so you literally can't get it wrong. It just proves that you are here, and in case you missed at the beginning of answering this question, you can answer it now. Good, people are able to click on it. All right, if anybody has any other questions, type them in the chat box and I will try to answer them. This is recorded. It's a ginormous file, so it's going to take a long time to compile. But once it does, I'll get it posted on our website. So if you got a coworker that wants to watch it or watch a certain segment of it, it'll be available on our website for you to do so if you wish. While you guys are doing that, let me just say on, I think it's Wednesday. Wednesday, let me check to be sure while you're clicking answers. Yeah, Wednesday, there's a bunch of stuff coming up for PDHs if you need PDHs. So in Central Time on Wednesday at 10 a.m., there is a HAP load calculation webinar that's worth 1 PDH. At noon, there's a HAP energy simulation 1 PDH webinar. And then at 1:30, I have another webinar on HVAC industry updates where we'll specifically talk about refrigerant changes upcoming, DOE efficiency ratings that are coming, and then we'll even dip our toe into some of the code changes and other stuff coming up. So you have an opportunity to get at least 3 PDHs on Wednesday if you are interested. And I'll put those all up on our website right now. I think one of them's already up there, but I'll put the HAP ones up there right now. Other than that, I'm going to close this poll. And I thank you guys for your time. And if no one has any other random questions, I am going to shut it down. Give it like a minute. Cool. All right. Nobody else had typed any questions in. So I'm going to shut it down, and maybe I'll see, or at least you'll see me on Wednesday. Thanks, guys.